Welcome. Let's continue the ziglings tutorial here. So hopefully I can finish this now. I think the first part should be quicker though, because it was like, you know, very basic, but I did go through, you know, my experience with Zig as well, so it took a little bit longer, but yeah, let's just continue here and see how, if we can hopefully finish it this time. Okay, so we are at exercise 70 out of, I think it was like 110, so there's 30 left or 31 left or something like that, one of our. Alright, so this is comp time, continuing with the comp time. Okay, so let's see. Being able to pass types to functions at compile time lets us generate code that works with multiple types. Oh yeah, so last time I think we ended off with a 69, which took a generic, well, it's a generic function which takes a type and also a comp time size and produces a slice of that size, and it also populates it with an integer. Oh yeah, so t has to be an integer in this case. Okay, well, that's what we did, so we're continuing here. So I'm just, you know, refreshing my memory a little bit on where we are. Being able to pass types to functions at compile time lets us generate code that works with multiple types, but it doesn't help us pass values of different types to a function. Alright, for that we have the AnyType placeholder, which tells Zig to infer the actual type of a parameter at compile time. Yeah, AnyType. AnyType is a special type. You cannot instantiate a type like alias to AnyType. AnyType is like a special, I think it can only appear as a parameter in a function. So it is kind of special, like that. Then we can use built-ins such as type of, type info, type name, has declaration, has field, to determine more about the type that has been passed in. All of this logic will be performed entirely at compile time. Right. Yes. So we're importing print here. Let's define three structs, duck, rubber duck, and duct. Notice that duck and rubber duck both contain waddle and quack. Methods declared in their namespace, also known as declarations or declarations. Okay. Duck, eggs, loudness, location X, location Y, okay. Waddle, quack. Alright, and now we have a rubber duck in bath, location X, waddle, quack. Listen. Aha, so duck programming, excuse me. I just sneezed there, sorry. Listen, yeah, so this is like the duck programming where you cannot, it's like you encounter some sort of hurdle or some sort of problem that you have trouble with, and there's been so many cases where someone just asked a question to another programmer for help, but as soon as they ask the question they realize the answer. That has happened to me multiple times as well, and it's so common that it's called like, it's a phenomenon called like duck programming. And the idea is that instead of taking time from a fellow coworker, you could I don't know why it's a rubber duck, but I guess it's like a common thing. I don't know. That you would place on your desk or something, and you would talk to it to say, ask the question, and you would then, that would substitute for asking like a real person. You would still go through the same, I guess, process and come up with the same like answer to the question. So, which is interesting. And let's see. So, I mean, you don't need a rubber duck for it though, but you can just, think a little, take one extra turn in your head to realize the answer. Okay, but I think there might be something like actually trying to formulate the question makes you think about it in another way, which then leads you to the answer, basically. Okay, anyway, and we have a duct, which is an entirely different thing. Okay, we can connect it to other ducts, apparently. Okay. Duct error, unmatched diameters, right. So we have a duck, we have a rubber duck, we have a ducky 3, which is not a duct. Okay, print ducky 1, ducky 2 is a duck. Okay. So this is like the generic function now. So this function has a single parameter which is inferred at compile time. It uses built-in typeof and has declaration to, or has decl to perform duck typing. If it walks like a duck and quacks like a duck, then it must be a duck. To determine if the type is a duck. And that's also clever, using this saying here. Is a duck, possible duck. Okay, so this takes any type. So basically you can put anything in there and it works kind of like template programming in templates in C++. So this type will transform into the type you put in, and it will also become a copy of the function with that type, replaced for this possible duck here and everything. And you can get the type like this. So this, the type is this, and then we use some functions here, built-in functions, to know what we're looking at and dealing with. We'll use has declaration to determine if the type is everything needed to be a duck. In this example, has increment will be true if foo has an increment method. Const has increment, has declaration foo increment. Yes. So this works for both functions, member functions, like static functions, member functions, or yeah, I guess they are also member functions, I guess. Well, static functions on a struct, and functions that are like non-static member functions, and also constant declarations. There's also constant declarations, mutable declarations that hasDecl can look for. And then you also have hasField, which look at fields, obviously. So those two you can look at the struct and quickly determine by name of the field or thing if it is there. So it's kind of a quick way of checking, like, okay, is this remotely like what we're looking for? You can do a lot more, you can be very specific as well, but then you won't use has declaration. You would use like proper type reflection and introspection on that. Please make sure my type has both waddle and quack methods. Okay, well, I will make sure that it has both waddle declaration, doesn't have to be a function, and quack. And I'm guessing we will get to more introspection like later, otherwise I can show that as well. Is duck, walks like a duck, and quacks like a duck. Then if we're a duck, we do this. We also call the quack method here to prove that sig allows us to perform duck actions on anything sufficiently duck-like. Because all of the checking inference is performed at compile time, we will still have complete type safety. Attempting to call quack method on a struct that doesn't have it like that would result in a compile error, not a runtime panic or crash. Yeah. Yeah, so if this type did not have quack, then it's not like, you know, it's not like we determine at runtime what these types are. The type is known at compile time. So if we call quack and the compiler wires it up, it knows where to call quack, like it knows where quack is. So it's not like this is like can fail at runtime by doing this. Anytime you have any sort of struct and you call a function on it, the compiler actually knows how to call the function there. Okay, well, is duck, then we call quack to, I guess, make sure that it is duck, and we return this duck. Yeah, it's also the possibility that the waddle quack are not actually functions, and in that case we have to do more introspection to know that it's a duck. Okay, let's see if that solved it. Yes, we're on to 71. Sorry, I almost sneezed there. It's so annoying when you almost sneeze and nothing comes out. There have been several instances where it would have been nice to use loops in our programs, but we couldn't because things were okay. Because the things we were trying to do could only be done at compile time, right? So I already did this, but we'll do it again. We ended up having to do those things manually like normal people. We are programmers. The computer should be doing this work. And inline 4 is performed at compile time, allowing you to programmatically loop through a series of items and situations like those mentioned above, where a regular runtime for loop wouldn't be allowed. Inline 4. So inline here basically means that we're unrolling the loop immediately. So yeah, so basically here we can see that we're looping through this list and we have 4 different elements. So this would unroll into this code where, you know, each instance would be replaced by the element like this. And then since this is compile time known, it would just, you know, resolve into some kind of number here. I mean, this would be just 8 and, you know, 8, 16, 32, and 64. So that's what it would compile into after this is done here, which is pretty cool because it's kind of like a code generation thing. And it's very useful for certain scenarios. So like looping through the fields of a struct to do something there, like yeah. Anyway, so in the above example, we are looping through a list of types which are available only at compile time. Remember Narcissus from exercise 65? Yes, I do. Where we used built-ins for reflection. He's back and loving it. Alright, so everything is undefined. Seems good. Okay. Narcissus has room in his heart for... And then we do stuff. Last time we examined Narcissus struct, we had to manually access each of the 3 fields. Our if statement was repeated 3 times, almost verbatim. Yuck. Please use an inline 4 to implement the block below for each field in the slice fields. So, here we're doing proper introspection here, or reflection here. So we're getting all the fields from this struct, which is also available if you do meta fields and just put the type in here. You will also get the fields out. but this is another way to do it. This type info basically, it returns a union enum of the type. And since we now know that this is a struct, we can just say, hey, it's a struct, and I get the fields. But if we do it like this, then we also get a list of fields. But this field, since the type that you pass in, there's 3 different things that can have fields, which are structs, unions, and enums. So you would get like different results depending on the type you put in. But since we know that it's a struct, it doesn't really matter in this case. But always good to know there. Okay, because otherwise you would have to like pattern match, or you would have to like match on this on the type info to see, okay, is that union, but the standard meta fields does that for you. Okay, so here we're doing an inline 4 on the fields, and we get a field out, and for every field we're checking if the type is not equal to void. Then we're printing the name of the field. Once you've got that, go back and take a look at exercise 64 and compare to what you've written to the abomination we have there. Well, I'm not going to do that because I believe I already upgraded that. Narcissist is a room for its heart for me, myself. Great. So now we're on to 72. There's also an inline while. Yeah, I think I never actually used the inline while. I didn't know that it existed actually, but that's interesting. Just like I wonder what happens if you like inline while true. Will the compiler crash? Or yeah, I mean it should probably figure out something is horribly wrong. Maybe, hopefully. Just like inline 4, it loops at compile time, allowing you to do all sorts of interesting things not possible at runtime. See if you can figure out what this rather bonkers example prints. Okay, so we've got const foo. So we have 3 pointers to strings that are all 5 length arrays. So is this the monkey example, or maybe, I don't know. Okay, so then we have the company var I equals 0 company comp time inline where I is less than foo.length I plus, I mean there has to be like a maximum iteration here. Yeah, I think there's like an eval branch max like quota or something that you can set. I'm not sure if this is part of that, but this is like a loop and not a branch, I guess. But anyway, inline while I is less than foo.length I plus equals 1, so it increases by 1. This is like a for loop, in the like a classic for loop here. And print foo I plus plus end line foo I. All right, because foo is comp time known. Okay. So yeah, so we're appending here, but wait. Oh, I see. Okay, so we're building this formatting string like this. So so we're building the formatting string, and this is the like S. This is where the string will end up from here. So it will be like 0, 1. No wait, I is 0, 1, 2. But okay. I'm just, my mind is kind of, okay, so it will be like it will look kind of like, so the result would be, first you would get the first one, which is this. Okay, but then this is replaced by this. So you would get something like this, I think. And then the second one is the same thing. Like this. And then the third one you would get that. I'm pretty sure. Okay. Yeah. And this would this would, I guess, yeah, it would unroll into 3 prints that prints out these things. Main. Here is a string containing a series of arithmetic operations and single-digit decimal values. Let's call each operation and digit pair an instruction. Ooh, nice. Here is I love these kind of programming instructions stuff. Here is a U32 variable that will keep track of our current value in the program at runtime. It starts at 0 and we will get the final value by performing a sequence of instructions above. This index variable only used at compile time for our loop. Right, because our instructions are comp time known, so we can potentially evaluate them at compile time. Here we wish to loop over each instruction in the string at compile time. Please fix this to loop once per instruction. Okay, so this would be like an inline while. And I plus equals to 1 because we need to go through each one, except this is a string. I mean, it would be better if it's like a array of instructions, but it's a string, so well, I guess it depends on, I mean, we're kind of parsing the string. So each instruction is like, you could say that each instruction is I would say it's 3 characters wide, but then the last one is skipped. So I would just say 3 there. This gets the digit from the instruction. Can you figure out why we subtract 0 from it? Because ASCII. It's converting the ASCII character of the ASCII character 3, which is like a specific, I think it's like 40 hex is the start of the alphabet, if I'm not mistaken. 60 hex is like, one of them is lowercase, another one is uppercase. But then 0 starts somewhere else, but I don't remember exactly. But yeah, but the point is that, I mean, we could do this. We could do I forgot how to do it. Zero. No. Actually, no. It's like this. You have this, and then char code at 48. To string 16. Okay, so it starts at hex 30. Yeah, so really when you're saying -0 like this, ASCII character 0, that really means negative OX30, or 3 times 16, which is 3248. Yeah, so it really means like -48. And the thing is that the ASCII characters are all lined up, so you have like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if we loop through we will, whoops, oh yeah, we will see that 0 no wait, yeah, so here we'll see that here is the ASCII character and here's the actual, you know, value in binary that represents. So 0 starts at 30. Well, this is actually hex, but 1, 31, 32, and so on. So if you subtract the ASCII value 0, which actually is hex 30, you would get back, you know, the actual number in binary. So that's why you do it. There we go. We went through the whole thing. Okay. Now, this switch statement contains the actual work done at runtime. At first, this doesn't seem exciting. Switch instructions I plus negative times else unreachable. Okay, but it's quite a bit more exciting than it first appears. The inline while no longer exists at runtime, and neither does anything else not touched directly by runtime code. The instruction string, for example, does not appear anywhere in the compiled program because it is not used by it. So in a very real sense, this loop actually converts the instructions contained in a string into runtime code at compile time. Guess that we're compiler writers now. See, the wizard hat was justified after all. Yeah. So basically this is all run in the compile time. So I think in the end, value is actually just set to some value through these instructions, and at the end here, I think this entire instruction could be optimized down to saying just value equals to the answer of this whole thing. Man, I'm getting so many false positives on the sneezing. Okay, so are we done? Oops. I think so, yes. 73. As a matter of fact, you can put comp time in front of any expression to force it to be run at compile time. Execute a function, comp time llama, get a value, comp time baz. Yeah, which is very cool because there's like standard library functions like checking if two strings are equal, for example, which takes like comp time strings into account. But any function can run in comp time as long as the parameters, the arguments are comp time as well. Okay, execute a whole block. Yeah, so this whole block is comp time. Get a value from a block. Yeah, you can even get like values out, which you can then use in runtime, which is cool. Llama count 5 llamas. Okay. We meant to fetch the last llama. Please fix this simple mistake. get llama. Okay, or even better, my llama value is that. Okay, get llama. We put a guard assert at the top of this function to prevent mistakes. The comp time keyword here means that the mistake will be caught when we compile. Without comp time, this would still work, but the assertion would fail at runtime with a panic, and that's not as nice. Yeah, it basically crashes the program. Unfortunately, we're going to get an error right now because the I parameter needs to be guaranteed in order to be known at compile time. What can you do with the I parameter above this to make it so? Okay, well, we can make it comp time, I guess. If this is asserted at comp time, then everything here needs to be comp time known. Alright. Fun fact, this assert, but now we changed it to comp time, so we need to make sure that this is also comp time. So, but this is comp time known. Array length is always comp time known, and then -1 is comp time known because it's a literal. Okay. Fun fact, this assert function is identical to std debug assert from the SIG standard library. Function assert. Yeah, but you can just go in here and look at it. Oh, wait. Oh, I thought they used the function. Yeah, this is all it is, which is nice. But it's also, I think this if you look at this is pretty interesting. This function here invokes detectable illegal behavior when OK is false. In debug and release safe modes, calls to this function are always generated, and the unreachable statement triggers a panic. So you're basically using it in, while you're developing, but then when you're compiling it to release it, the assert calls are deleted basically. But so the idea is that you would test your program in development, and then you would see that okay, all the asserts are fine. So we could just remove them because they are unnecessary checks in that case. But it says here that calls to this function are optimized away, and in fact the optimizer is able to use this assertion in its heuristic. So if you're asserting yeah, I don't really know an example of this, but apparently the compiler can like optimize things based on the assertion. So they are not just, sanity checks. They can actually be used as, optimizing some stuff. But I don't actually know any examples of that. Okay, so fun bonus fact, I accidentally replaced all instances of foo with llama in this example, and I have no regrets. I see. Let me fix that. Okay. But now I have to say there we go. Okay, now we're on 75. No, wait, what? 75. What about 74? Skipping 74. What? Okay, we'll see. In addition to knowing when to use the comp time keyword, it's also good to know when you don't need it. Following contexts are already implicitly evaluated. I will say about comp time, I think that I required like a lot of practice before I actually got comp time, like knowing when, like getting an intuition of when comp time is good or needed versus where you have to use runtime and so on. I mean, you would think that is probably a little bit, self-explanatory, but the language has some quirks and stuff, and sometimes it feels like, oh, but this should be able to be comp time or runtime or whatever, but then it just doesn't work. But yeah, I required a little bit of practice, or I would say a lot of practice before I kind of built a good intuition of it. So, but once you have it, it's really nice. In addition to knowing what the following contexts are already implicitly evaluated at compile time, and adding the content keyword could be superfluous, redundant, and smelly. The container level scope outside of any function in a source file. Yeah, everything there is comp time, but the compiler will tell you as well type declarations of variables, functions, structs, unions, enums. Any type evaluations, like evaluating or resolving a type is always done in comp time. The test expressions in inline for and while loops. Test expressions. Oh. Wait, are they comp time? That's weird. That doesn't make sense. Test expression, like you would have to test the runtime current value. Oh wait, in inline for and while loops. I see. Inline, yes, that's the keyword. Yeah. Okay, yeah, that makes sense. Inline in the test expression. Yeah, because you have to unroll it, so. What about continue expression? Is that also comp time? Because you would need to unroll that as well. I mean, that might not actually be comp time. I don't know. An expression passed to the C import built-in, which we haven't gone through yet, but it's basically a way to import C libraries, which is really, really cool. And get like native Zig support for C. Like you can import C libraries and use their functions, and you get like LSP support, and yeah, it's really cool. Let's see. Work with Zig for a while, and you'll start developing an intuition for these concepts. Yeah, that's what I'm saying. Let's work on that now. You have been given just a comp time statement to use in the program below. Here it is. Comp time. Just one is all it takes. Use it wisely. Okay, so they're saying like I should try to only use one comp time statement, so we know that this is comp time. Being a container level scope, everything about this value is implicitly required to be known at compile time. Well, it's a literal. It's a constant. It doesn't depend on any runtime values. Yeah. Again, or any other values for that matter. Again, this value's type and size must be known at compile time. Hello, Blue. Welcome. I mean, yeah, it's fun. It's also nice to, you know, as I've said before, like cover all the bases of Zig. I never went through, you know, looking at like all the features and stuff, or going through all this beginner tutorial. You never know what kind of tips and tricks you might snatch up here. So I'm just gonna finish this here, and we'll see what happens after that. Again, this values type and size must be known at compile time, but we're letting. So how are you doing, by the way? We're letting the compiler refer both from the return type of the function. Yeah, so this is still in compile time because we're outside of the scope of a function. And so this call here is automatically, you know, in compile time context, and so this will be some sort of compiler error. if something in here doesn't work. And since this function isn't called anywhere else, we can just make this comp time, and there we go. I think that should do it. The lesson here is not to pepper your program with comp time keywords unless you need them. Between the implicit compile time context and Zig's aggressive evaluation of any expression it can figure out at compile time, it's sometimes surprising how few places actually need the keyword. Okay, so it's says link, it's skipping this. I guess maybe it's because it's like a compile time, so, but it's still, I mean, we're printing. I don't know. Okay, so skip that, I guess. Hopefully that was correct. Quiz time. Let's revisit the Hermit's map from quiz 7. Oh, don't worry, it's not nearly as big without all the explanatory comments, and we're only going to change one part of it. Okay. Yeah, so I think we have basically the same stuff here. Remember how we didn't have to declare the numeric type of place count because I only used at compile time? That probably makes a lot more sense now. Sure. Okay, so as you may recall, we had to create each path struct by hand, and each one took 5 lines of code to define. Somehow you managed to get bugs in a simple tic-tac-toe game. I mean, it happens to the best of us. Oh, that's cool. Is it in Zig? Right, each one took 5 lines of code. Yes, from to distance. Well, armed with the knowledge that we can run code at compile time, we can perhaps shorten this a bit with a simple function instead. Please fill in the body of this function. Ah, now it's a little bit more open-ended. I like these kind of puzzles. So we have from to return a path, so we will return this path. I mean, we already have the answer here, so I mean, there we go. Using our new function, these path definitions take up considerably less space in our program now. All right. Yeah, good place to start. How, like on the terminal, or using like Raylib or something? Using our new function, these path definitions take up considerably less space in our program now. A paths, B paths, C paths, D paths. Ah, I see. Yes, they do. All right. But is it more readable? That could be argued either way. Yeah, I mean, so for this to be readable, I guess if you compare it to the other example where it like stated each thing immediately, the only thing you need to do here is go and look at what makePath does. And now you have an understanding. Once you have an understanding of that, you go back, and now you basically have condensed the previous information that was in the first, example. But that's the crux of it. You have to go and look at this now. But I think that's probably worth it in this case. I think this is a very good upgrade. We've seen that it is possible to parse strings at compile time, but there could be argue that if you make too many of these helper things, then is it more readable? I don't know. It all depends, I guess, on everything and who is reading the code as well. I guess but if you're the only one working in your project and you're kind of used to, and you're working in it all the time, Well, that's both bad and could be good for productivity, but it could be bad as well because you usually get lazy. Well, at least I do get lazy, and you come back to the thing sometime later and you're like, what the hell is happening here? This is a mess. I use reader interface take byte, something like that, to take console input. I'll try Rayleigh next. I already made Snake Game Rayleigh, but in C. Oh, okay, cool. All right. So you're like printing, or you're printing like a new like representation, like ASCII representation of the tic-tac-toe board, and then you take an input to show, or to, yeah, you take an input, instruction input, and then you print a new board. But is it more readable? That could be argued either way. We've seen that it is possible to parse strings at compile time, so the sky is really the limit on how fancy we could get with this. For example, we could create our own path language and create paths from that. Something like this, perhaps. Okay, I see. Wow. Okay, well, that's ambitious. I mean, is this more readable? Okay, this jumped way ahead in, you know, in, I mean, I guess it kind of comes from the instructions they had before. So if you would have that, you would have like paths. Now let's have these lines. I guess we would have to use like these. Yeah, let's just do this. And then U would be A to B, I guess. A to B 2. Why is there like square brackets here? So this would be like A to B. I mean, let's just follow their example here. A to B2. B goes to A, 2 and B1. C. I use ANSI code colored on the terminal. Oh, nice. And if you want to make it more, I mean, yeah, I recently learned about what are they called? CSI, or yeah, that sounds like something like a popular TV show, I think. But like CSI codes or CIS, no, CSI, yeah, something like that. I think this is just a fun exercise. Because I'm currently, you know, I'm currently playing around with building like a parser in Zig for random languages. C goes to D with 3 and E 2. I mean, yeah, sure. This is, I guess, more readable. I guess. B1 C. 3. E goes to C2 F1, and F goes to this is actually kind of interesting because I never really thought about doing it like this. It goes to D7. So this is the instructions or the paths. Now, okay, so let's try and make like a parser for this, or like a, you know, executing this to make some paths. So these are the paths source, maybe I can say. And then let's make a var paths, which I mean, I guess this would be like a array or slice of paths. And since it's like compile time, so we can set it to be an empty slice and then change it later. So we're in compile time context now, so we don't have to like specify compile time here. Now let's also, well, we could make a block, I guess. And actually what you could do is you make this constant and then have a break clause and do this, and here we'll make paths this, start with that, and then we'll break, when we're done, we'll break this result here. Actually, I call this out. All right, and then we will have an index I, start at 0, and we will inline. I'm not sure if you need inline here because we were already in a comp time, but sure, we'll do inline to see how it can work here. And then we'll say, no, not for, while I is less than path source length. So path source is just a string, but it's like a multi-line string. So each line here that's after this slash slash backslash backslash, this is like this string and then an end line, this string and an end line, and so forth until the end here. Okay, and then I is, I mean, I guess we don't really have a continue expression that is, we can, I mean, I guess we could have a dynamic thing. We could have like how far ahead should it jump, maybe. So what would this, we call this like a drop or something, or skip, not skip. Well, I don't really have a good so we'll start with how many, like the arrows here. So this would be like I plus equal to skip. So now we can change skip depending on. Okay. So first we'll take from, which should be path source I. So that's from, that's gonna be like A. And how do we get A now? Well, we have these defined up here. I guess we'll have to have like a mapper from char to place. Whoops. Taking a comp time char, getting a place out, and, or I mean a pointer, and then we will just switch on this and we'll say if it's A, then return A, if it's B, and so on. So let's just, we'll grab all, where are they here? Okay, and we'll return that. So now we have a way to get the place. And we need to parse the destinations. So from needs to be chart to place. So there's that. I guess we'll put else invalid place. I have to put it in a string, or I mean a slice, and like a slice there, yeah. So yeah, that's our place. Actually, I want to move this down here so we can see what's going on, how the format looks. Okay. Now then we want to skip, so we want to say what you also could do is you could have an enum what current thing we're reading is. So let's have a state, and this one is an enum. You can define a type on the fly like this. So you can have like, first we're reading from, then we're reading destinations. Okay, so first it starts at from, and we can now do a switch. Actually, instead of inline while, we can actually use like a labeled switch statement, but I'm gonna do this for now. So we'll say we'll do a switch on state. If we're currently reading from, then actually we should have this first here. From, and then destinations should be a list of places. Okay. Now first we're setting from to that, and then we're changing state to be destinations. And we'll skip, you know, 1, 2, 3, 4, 5, 6 characters. And then we do a continue. If we're reading destinations, okay, actually this should be 2 and then distance and then more, I think. So take 2. So now we should be at the 2 part. 2 equals chart to place 2. Then we'll skip 1. We'll set state equals to distance. We'll skip 1. And now we're reading distance. And we need a distance. Actually, destinations need to be like a struct of place And distance. What was distance again? U8. Is it necessary to have master branch installed to try ziglings? I'm on 0.15.2. What? 0.15.2? I didn't know that was released. Okay, so 0.15.1 is the latest, I guess, like stable release. And well, the answer to your question is no. You can actually choose which version you're gonna use. I think they update ziglings each version. And okay, so what I did was I did like this. First, I cloned ziglings like this into a folder or directory called ziglings. Let me copy this. And then I did something with git. No. Git like yeah, okay, let me look this up here, because you need to specify a certain commit. And I close that thing. Let me see here. Zig. Where did that go? One second here. Ziglings and tags 0.15. Yeah, and then this is the commit here. So you would say then it's like git change to specific commit. You would say I mean, okay, so there's apparently different ways to do it. You could do like git reset and paste this in. This is the commit, that's the commit there, the commit hash. So that would put you to the version that is compatible with 0.15. All right, so we need destinations. These are a series of places and distances. We're reading 2. Now 2 we don't actually have. We need to add a new destinations here. Actually, we should have like a current destination. This is very convoluted here, but let's make this annullable. Let's make this a type destination. This is a nullable destination. Okay, started null. This is a list of destinations. So if current destination is equal to null, we will set current destination to a destination where place is equal to chart to place, or let's just set it to undefined for now. And then we will set current destination dot place is equal to this, and then we're reading the distance, which we should basically do the same thing here. Actually, this should be like skip 2, right? So we're reading the destination. The distance. And this would be this. And I guess the distance can technically be, you know, 8-bit, but I'm just gonna say that it's never gonna be larger than 10 or than 9. So it's gonna be 9. So it's just gonna be one character, just to make things simpler here. So distance is now we're here. Now we need to jump ahead 2 and then read if we have more. So we'll set skip state to more, skip to 2, I think. So we're over here, jumping 1, 2, now we're over there. So we need a more state. And I mean, all in the case of making this more readable, right? But yeah, it's kind of cool that you can do this like in comp time. Yeah, no problem. Let's see, so if we're reading more, actually I'll put this in a thing here. So now we're at here. 2 means we are over here. Distance means we are over here. More means we are over here. As we have 2 scenarios where we could have something like this. So if path source I is equal, so the first thing we want to do is we want to say that we should add a new destination. And how do we do that? Well, we say destinations equal destination, and we append the current destination to that. Now, since this all done in comp time, you can do this here. So we're basically extending, we're appending to this slice. Next thing we should do is set this to null, so we're resetting that, so now we can accept a new destination next time. Okay, so now we're checking next is that, so if next is equal to this, that means actually we could do a switch on this, and if we have this, that means we skip 2, I believe. Skip equals 2, and then we continue. Then we just end and do the next one. And we also have to set state to from. Otherwise, we have this, which means we have more destinations. So state should be set to 2, and skip should be, so we're here, so we should skip to ahead and then continue. We don't have any white space handling here. We're just, this is so static. If you do anything out of the ordinary here, it will just completely crash. But at least we have a readable way of doing this now. Okay, so yeah, and then else should be unreachable. Or I guess we'll have like a compiler error saying invalid character. We can just say, actually we can just say like I plus 0 as u8 cast. Couldn't we do that to transform it? No, because it needs, it's like, okay, no, that doesn't work. But we can use format comtime print char at that, and we'll do this, and we'll say format I. No, first we have paths. Source I, and then I. There we go. All right. State is from. Here state is 2. Read another destination. Skip to continue. All right. And if, yeah, and then if we're done, we should just end. So now we should have like a list of paths in this list, and I guess what we could do is we could, you know, this is a lot of stuff going on here, so probably we should see if it actually works. So we could do like inline 4 paths, and we could do a compile log and do a compile print, and we can say, actually we need to import this guy. Come on. So we're gonna have path from something. Now this would be S. Actually, this is like comp time known, so we could just say actually let's just do now we could make this the other way around. Where was the thing? This one. Let's make this the other way around as well. Place to char. And we'll just make this the other way around. So and this is a place. Return a char if place and invalid place Oh yeah, this needs to happen in like a... okay, let's do this. Yeah. Redundant inline in content scope, unused capture. So then we'll use path to, or place to char. P is a path. No, it should be pointers, right? No. These are paths. Oh yeah, so this is like from. There we go. And path from this to this distance this. And distance. There we go. This is never mutated. Right, okay. So when we're done here, yes. So when we're done here, we need to set this to a new path. Where from is from, to is to, or I mean, wait. Oh yeah, we need to for on destinations. That's right. We have a list of destinations, so we need to look through them. For each one, we append a path. To is destination place. Distance is destination distance. Okay. Now, and also here we need to reset this to back to nothing now. There we go. So we're adding our paths to the result, and we're resetting the destinations as well. And so now that should be fine. And current destination was already reset, I think. Yes, that's reset no matter what there. Okay. This is redundant. There we go. Now, let's see. Should we now... Let's see, where is this used? Oh, wait. Okay, this is all the same, like the notebook entry and all that. And now we're down to main. Okay, so they're doing some stuff here. So I guess they're trying to make it... okay, so they're saying... What's happening here? We have letters, A, B, so a list of characters. Actually, these are strings, a list of strings. A list of strings. And we're taking each string and we're field on this. What is the... Oh, this... Okay, this is interesting. This is actually pointing to the file. Okay, I never thought of that. So, oh yeah, so these are actually declarations, like... I didn't think about that. So these are actually declarations in the struct that is the file. The whole file is one giant struct. Everything is a struct, basically, almost. No, but each file is its own struct. These are declarations in the struct, so you can access them using @this in the file level, in the top level, and using like field accessing with those. Okay, Yeah, I didn't think about that. I mean, I will keep my things as they are because I don't want to change it right now. But okay, so you can do this as well. So that's nice. What are we actually doing here? We're setting paths to underscore paths. Oh, we're populating paths like that. All right, I see. I see. Okay, we can actually change our code to do that as well. But I'm just gonna try and see here, figure it out. Okay, so we'll call to make this code run basically. So I'm gonna do this. Go back here. I'm gonna look at paths and do this, because now we should get a bunch of compile logs from that, hopefully. So let's look at that. No. 95. Oh, this can't be undefined. Okay, well, what if we just set these to undefined like this? And then you are this. Actually, we will never have this be null if we're currently reading the distance. I'll just remove that. All right. Unexpected indexable found this. Okay, so 113. So we're trying to append to. So this is also a little bit of a problem with this. So I think the problem here is you need to actually type this here. So this is it's not a question mark destination. This is a destination. So do destination like this, and I believe this will solve the problem. No. Expected type found const. Pointer to a constant array. I thought it could like coerce it. I'm pretty sure there's some way of doing this. I'm gonna change you to maybe this needs to be like const here. Okay, that fixed it. Quote unquote fixed it. I'm just gonna grab something to drink here. We are back. All right. Yeah, and this is the same issue. Line 800 or 118, and this is a path, and you are, I can change you to const. That's fine. Comp time place. $273. Okay, yeah, this now this should be an inline 4, because now we're not in comp time context anymore, we're in the main function. Cost discards const qualifier. Alright, so oops, we'll make you take a const place and comp time value, comp time print. Okay. So these are constant, these are comp time known. This should be, I wonder if you do this. No, it's redundant, okay. What is your problem? Unable to resolve comp time value. Where is this happening? 273. Yeah, it's here. So which one is it talking about? Function return type must be comp time known. Yeah. And these are. Well, this one should also be comp time because the source is comp time known. Okay, let's divide this up. And we'll see where the issue is. Six, 5, 8. What? No. 2, 7, 3. Oh, so it's the first one. But it is comp time known, though. Can we make the function comp time? Function return time must be comp time known. But it's comp time print. Do I have to say like comp time like this? Okay. Okay, well, I mean, we got a result here. So you can see here we get some compile logs. Never mind all the weird warnings here. But you can see here now that, okay, if we go up to the paths instructions, so we built basically a comp time parser that parses this string and makes, you know, builds a bunch of structs from that. So we're saying A goes into B2, B goes into A and D, yeah, and so on. So all of these are now being produced here. So A, so this is from A to B and so on. Let me fix this output. Okay, so we got from A to B distance 2, from B to A distance 2, and B to D distance 1. So let's see if that is correct. A to B distance 2, B to A distance 2, and to D distance 1. Yeah, so we basically built this parser now. That was kind of fun. Yeah, and it's all done in compile time, and so no actual runtime code is gonna be doing all this crap here. So that was pretty cool. So we basically done a little, you know, domain-specific language within Zig, which uses compile time to generate code from this string. That's, I mean, that's pretty amazing actually. Yeah. Okay. Now. Okay, so I'm happy with that. Now, what is the actual issue here? Okay, we passed it, I guess. I'm not sure where the problem was. I think we solved it along the way. Okay, let's just continue here. 76. Sentinels. A sentinel value indicates the end of data. Let's imagine a sequence of lowercase letters where uppercase S is the sentinel, indicating the end of the sequence. A, B, C, D, F, S. If our sequence also allows for uppercase letters, S would make a terrible sentinel, since it could no longer be a regular value in the sequence. Oops. Yeah. A proper choice for indicating the end of a string is the value 0. ASCII and Unicode call this the null character. Zig supports sentinel terminated arrays, slices, and pointers. And you put a colon 0 to denote that it's a 0 sentinel. And I mean, this is basically the extent of the usage that I've seen this to be used for. I've never seen it used for anything else than 0 terminated strings. But, you know, I haven't seen everything, so... But, you know, it's I guess I would say, like, the most common use of this would be 0 terminated strings. And especially if you want to interface with C strings, then it's, like, mandatory, like, to use this, because... somewhere in your code, because you have to like deal with those strings and they are 0 terminated. So okay, so we got A is a 4 array with 4 elements and 0 terminated, and the definition here looks the same like the value here, but they sneakily hide a 0 at the end here. The compiler will add that. Okay, array A stores 5 U32 values, the last of which is 0. However, the compiler takes care of this housekeeping detail for you. You can treat A as a normal array with just 4 items. Slice B is not only allowed to point to 0 terminated arrays, but otherwise works just like a normal slice. Pointer C is exactly like the many item pointers we learned about in exercise 054, but it is guaranteed to end in 0. Because of this guarantee, we can safely find the end of this many item pointer without knowing its length. We can't do that with regular many item pointers. Important. The sentinel value must be of the same type as the data being terminated. Yeah. Because it's part of the array, so it has to be the same data type. Here's, or the same size at least. Here's a zero terminated array of U32 values. Okay, and here's a zero terminated many item pointer. Right, so here we don't know how many items there are, but you know, I'd never use these. These are like, I don't really see a reason to use these. I mean, I guess there would be some niche instances maybe. I mean, it probably has its place somewhere, but so far I've never really stopped and thought, this is where I will need a many item pointer. I usually always use like slices. Yeah, that's what I use, slices or array lists for things. I mean, I think this is more common if you're gonna interface with C stuff, maybe. I don't know. For fun, let's replace the value of position 3 with sentinel value 0. This seems kind of naughty. Okay. Yeah, so we're basically saying, okay, we're now the end should be at index 3. So now we have a zero terminated array, many item pointer to reference the same data, a sequence of numbers that both ends in and contains the sentinel value. Yeah, okay. Attempting to loop through and print both of these to demonstrate that they are similar and different. It turns out that the array prints completely, including a 0 in the middle. Many item pointer stops at the first sentinel value. Oh, wow. I actually didn't know about this. That is interesting. I mean, okay. That's actually, okay, this is a use case. Because the thing is that I thought for a long time that slices was actually doing this. Well, or that they should do this. So instead what you need to do is if you have a slice that, okay, let's say you have a buffer that is like U8 something, but it is zeros terminated, and then you have a slice that has like, I don't know, some items from there. But now you say buffer 2 is equal to, or 3 or something is equal to 0. Now this slice like sort of counts that 0 into its data for some reason, even though it's like, it should be, okay, let's do this instead. This should be 0 terminated. So I was like, okay, when you print this, why are you showing the 0? It should be a 0 terminated string. Why is that showing the 0? I didn't know this, so okay, so apparently if you do this, you will actually 0 terminate it, like when you print it. Huh. Okay, that's a new thing. Because in the UI programming I'm doing with Dear ImGUI, which is a C library, we're using like 0 terminated strings everywhere. But it went so far, so I actually made my own string struct, so I don't really deal with this anymore. But that's very, very interesting. I still don't know why. I mean, it's a 0 terminated sentinel, so why would it like include the 0 in the like? Oh, okay. So now there's probably a good reason for it, but it just feels wrong to me. Now we have a 0 terminated array, many item pointer, refers to the same data. Sequence of numbers, both ends in and contains the sentinel value. Attempting to loop through and print both of these should demonstrate how they're similar if it turns out that, yeah. So why though? Why is it like that? Okay, well, the array prints completely, including the sentinel. Okay, the array does it because it has like a length. But it also seems strange to some degree that the array would do that. Oh yeah, now I remember. It was actually the JSON. Yeah, when you're serializing to JSON with the standard JSON library, if you have a serial terminated string using a slice, it will actually just print the whole thing. I think that's how it worked, and I was so annoyed by that. So what you would do instead is, if you have that and you want a pointer to like this slide, let's say this is nums, you could do what is it, mem slice 2 or span, I think. Yeah, so this one you could put in, or you could just do it here directly, but you put in span, so that will produce a slice that takes the zero terminator into account, or the sentinel into account. So it takes a sentinel terminator pointer and turns a slice, iterating over the memory to find the sentinel and determine the length. Pointer attributes such as const are preserved. Yeah, so you get a new slice that is guaranteed to only have the thing that is yeah, up to the sentinel there. All right, here's a generic sequence printing function. It's nearly complete, but a couple of missing bits. Please fix them. Okay, type info, containment, type is union. We use a switch to handle printing array pointer fields depending on which type MySec was passed in. Array, print array, loop through the items in MySec. Okay, so we're switching on my type. We're getting, if we see an array, we loop through. Oh, I see. So we have to sort of, okay, so we know that MySec is an array, so we can just loop through it like this. And then yeah, that should be fine. And if it's a pointer, we can get the sentinel, which is a built-in function that gets the sentinel from whatever you pass in. And so that's a value of the type. Yeah, that's the sentinel value. And then I guess we'll loop through until we get it. And here's where you could use a span instead, but yeah, here we're doing it manually. So loop through the items until MySec, in MySec until we hit the sentinel value. So while MySec sequence I is not equal to my sentinel, we will print that. There we go. Else unreachable. Yes, that seems to be good. Now we're on 77. Sentinels 2. Top secret! Are you ready for the truth about zig string literals? Here it is. Type foo. Okay, which means a string literal is a constant pointer to a zero terminated or null terminated fixed size array of U8. Now you know you've earned it. Welcome to the secret club. Okay, thank you. Why bother using a zero null terminate? when we already have a known length. Versatility. Zig strings are compatible with C strings, which are null terminated, and can be coerced to a variety of other zig types. Yes. You can have an array, I guess. Wait, I didn't know you could do this. Holy crap. What the hell? Yeah, initializing an array, like a string array like this. I did not know you could do this. Wow. Okay, that's new. Well, I won't really write it down because I'm probably never gonna use it, but it's useful if you want to have that sometime. Okay, b const 16u8 pointer. Okay, I'll be right back. 1 second. All right. Let's continue. All right. What I've got 5 array pointing to a constant array of 16 U8s. I mean, I thought this was like impossible. Like this was like a compiler. Yeah, you have to sort of make a. I don't know. Maybe I'm dreaming. C is a slice to constant U8. So an immutable slice, or yeah, the contents are immutable. Zeros are terminated, constant string here. A many item pointer to 0 sentinel string, constant string, immutable string. Many item pointer to immutable string. All but F may be printed. A many item pointer without the sentinel is not safe to print because we don't know where it ends. Yeah. There's no way of telling where it ends. I guess one thing you could do is look at printable characters and abort whenever you reach. But that's kind of like, yeah. Assuming weird container data has a pointer to, yeah, so this is more like the classical pointer from C, where you just point to something and you have no idea what's in there, except you know it's like a, it's, the compiler tells you it's a well, it's a point. It's, yeah, this is more like a classical pointer because you don't know if there's any of these items in there. You don't know if there's one. There could be several. Like, you don't know how much is allocated at that location. You just have a pointer to a place. I was thinking of an analogy in real life. Like, I thought that, oh, maybe it's like pointing to a box, but that's not true either, because you can kind of see the size of the box, so you would know how many items would be in there. You don't even get a size. Like, it's like pointing to, like, you would know where to go to look, but you wouldn't be sure that you're allowed to either. Yeah, I don't know. I don't know about a real life analogy for that. Main, weird container is an awkward way to house a string. Being a many item pointer with no sentinel termination, the data and field loses the length information and the sentinel termination of the string literal weird data. Luckily, the length field makes it possible to still work with this value, if you trust it. How do we get a printable value from foo? One way is to turn it into something with a known length. We do have a length. You've actually solved this problem before. Here's a big hint. How do you remember how to make a slice? Okay, so are you saying we can do data 0 to length like this? Assuming the length is correct. Yep. Great. We were able to get a printable string out of a many item pointer by using a slice to assert. I mean, and that's, you know, it's interesting, this example, because you could just as well use a slice, like, yeah, I guess that's why they're calling it weird, but it would be nice to get like a real example of where to use it, because I haven't really gotten to use it yet. I guess mostly maybe in like C integrations, maybe it could be used, I don't know. We were able to get a printable string out of a many item pointer by using a slice to assert a specific length, but can we ever go back to a sentinel terminated pointer after we've lost the sentinel in a coercion? I mean, yeah, because the data is still there. So you can just, if you know that the data is correct, you can cast it back into the pointer. Like casting a 0 terminated into a normal slice, you know, you don't do anything with the data. It's not that the 0 disappears, and then you can just cast it back. Same if you start out with a slice and you add a 0 somewhere, and then you make a 0 terminated slice from that. That's also valid. Yes, we can pointer cast that changes a pointer to another pointer using some comp time magic and validations and stuff. See if you can use it to solve the same many item pointer problem, but without needing a length. Okay, so here, this, I mean, are you saying that this Has a zero terminated now? This feels weird. Again, we're coerced. We've coerced that zero terminated. The sentinels terminate the string to a many item pointer which has no length or sentinel. Yes, so this has no sentinel. Please cast data to printable. But okay, now I'm confused because this doesn't have a sentinel, so where would the zero wouldn't be there, right? Or am I what am I missing here? Or is it because this is a const, so we can actually append the zero somehow in this, in like a copy here? I don't know. This feels wrong here, because there's no zero here. Like there's no, like, since this is not zero terminated. Like, what if we said this? This wouldn't work, right? Hang on. I don't understand this. I mean, the only thing I can think of is that the compiler just adds a zero here at like, it makes a new string and adds a zero to the end because it's all in comp time here. That's all I can think of. But you can't, I mean, it's weird to show this because I don't think you can do this with runtime values. You have to have a zero here. You have to know that there's a zero at the end. Okay, whatever. Let's just continue here. Sometimes you need to create an identifier that will not, for whatever reason, play by the naming rules. Okay, you can't start with a number, but you can do this. Illegal starts with a number. Const isn't true. Well, illegal. What even? If you try to create either this under normal circumstances, a special program identifier syntax security team, pissed, will come to your house and take you away. Thankfully, Zig has a way to sneak into these wacky identifiers past the authorities. The double quote identifier coding syntax. Yeah, so you can have basically anything in there, as far as I understand. Please help us safely smuggle these fugitive identifiers into our program. I mean, okay. I should have done a macro or something. Okay. Yeah, that works. It's like, it's good to know, but it's also like, I never use that. Struct types, but it is used in the standard library now, so it's good to know what it is, so you don't see it and you're like, what the hell is happening? Struct types are always anonymous until we give them a name. Struct. So far, we've been giving struct types a name like so. Foo equals struct. The value of type name foo is filename.foo. Yeah, so the declaration of which it is assigned to, like the identifier here in the file. A struct is also given a name when you return it from a function. Function bar type return struct. Store the struct type. Create an instance of the struct. Yeah, so it always go back to the original, which is very good because otherwise it will be super confusing. That's a problem in TypeScript actually, because in TypeScript it's like there's no concept of like an original type name, and so sometimes there's an issue where they print like error messages, or you want to know the type of something, and it kind of has to decide based on some heuristics or something what would be the best type name to display. Which is kind of fun sometimes. You can also have completely anonymous structs. The value of type name struct is file name, function, struct, and then some number or something. Yes, okay. This function creates a generic data structure by returning an anonymous struct type, which will no longer be anonymous after it's returned from the function. Okay, yeah. It's kind of weird of saying it like that, but yeah. I mean, I see it sort of like one type. This entire type is a circle. It's a generic type, so it's a function that takes another type and will return a type. Whatever type is returned is the circle T. Like, yeah. Okay, so main, see if you can complete these two variable initialization expressions to create instances of circle struct types which can hold these values. Circle 1 should hold I32 integers. F32. Okay. Perhaps you remember the narcissistic fix for the type name in example 65. We're going to do the same thing here. Use a hard-coded slice to return to the type name. That's just so our output looks prettier. Indulge your vanity. Programs are beautiful. Use a hard-coded slice to return the type name. What? Oh, the file name. Okay, yeah, we're stripping out the file name. My type. But it's already done, right? We're going to just use a hard-coded slice to return the type name. Would be an instant red flag in a real program. Yeah, so I don't think we need to fix anything there. Okay, there we go. I was like, what do I have to do here? An anonymous struct will value literal, not to be confused with a struct type uses dot. Yeah, so that's an actual value. Now we're instantiating a value of the struct and not the struct type. These literals are always evaluated entirely at compile time. Right, if everything is compile time known, the circle, the example above could be coerced into the I32 variant of the circle struct from the last exercise, or you can let them remain entirely anonymous as in this example. Okay, yeah. So you have any type, you can pass in anything, you can make whatever struct you want here. And this is also kind of special because you're not even specifying a type here. It's just inferred by the thing you put in. So, which is really nice because I would hate to have to put the type in there every time. The example above prints A true, B false. Okay. Print circle. Okay, so here we'll take, I guess this should be any type. Is that what you're trying to tell me? And what Oh yeah, so this is the circle. Okay. There we go. 82. You can even create anonymous struct literals without field names. Oh, so these are tuples. We call these tuples, which is a term used by many programmers. So they actually have field names. It's just that it's implicit. Yeah. To make this possible, Sig compiler automatically assigns numeric field names 0, 1, 2. So it's the same as saying like this 0, 1, 2. It's just that Sig automatically does that. So it's actually exactly the same as a struct. I guess almost. There's some special things you can do with tuples. You can deconstruct them, which is nice. Since pair numbers are not legal, identifiers is a syntax. We have to quote them with a So that's how you would access them. But there's another way to do it. I wonder if they will go through that. Like deconstruct, you can use deconstruction instead. If a thing is what the print function wants, do we need to break our tuple apart and put in another one? No, it's redundant. Oh, okay. Well, this basically never comes up. Like you could do this. I mean, I guess if you have a tuple, sure. But this usually never happens. Aha, so now we know what the print takes a tuple. Things are really starting to come together now. Okay. A tuple, we have some values. We're implementing this function. Let's make our own generic tuple printer. We should take up tuple, print out each field in following format, name, type, value, example. Okay, so we have the example here. Wait, hold on. Take a tuple, print out each field in following format. Yes, you'll be putting this together. Don't worry, everything is documented. Get a list of fields in the input tuple. You'll need type info. Yes, okay, I'm all familiar with this. This will be an array of struct fields. I mean, I want to use this. You could all, okay, whatever. Let's just use the thing. What is it? Tuple? No. Loop through each field. This must be done at compile time. Remember inline loops? Yes, I do. There we go. Print the field's name, type, and value. Each field in this loop is one of these. Yes, note that we learn about any opaque type later. You'll need this built-in field. The first problem, yes, I know about this. So print first is the name, then the type. No, wait. What did you want? Oh, yeah, it is the type. But the type has to be type named, right? I'm pretty sure. I mean, I guess we can try just putting a type there. I guess it will figure it out. And then this is the actual value, which will use field on tuple field of name. No, we got something at 85. Oh, it's not a... No, wait, it is a struct, right? Tuple is a struct. I'm pretty sure. Yeah. What's the error here? Expected type found struct. Oh, I see. This needs to be type of, type if, type of. There we go. So we got 0 bool true, 1 bool false, 2 either 2, yeah. 83. Anonymous struct literal syntax can be used to compose an anonymous list with array type destination. Let me read that again. Anonymous struct literal syntax can also be used to compose an anonymous list with an array type destination. Right, so the destination is this here, which is a type of 3u32. And this is how you could define this array value, which they call an anonymous struct literal, which is a tuple. But in this case, it's all the same type. The elements are all the same type. Otherwise, it is a tuple. Okay, so if we don't specify the type, it's a tuple. The only difference is the destination type, right? Please make hello in a string-like array of U8 without changing the value literal. Don't change this part. Okay, well, I don't think you could put, I'm not sure if you could put variable length here though. So you have to count it. There's, yeah. 1, 2, 3, 4, 5. So this should be 5. Right? Yes. Why is it skipping so many? Oh, it's the async. Aha, so we actually don't do those because there's no async. I wonder what it will say here. The memory space allocated problem for invocation of function. All data is called a stack frame. The return keyword pops the current function invocation frame of the stack is no longer needed and returns the control place where function has been called. Suspend. Oh, so the keywords are in there. And I guess they will like skip. You can assign things to underscore, but it returns as void. Okay, I guess these are not used. Okay, so we're going to interfaces. Oh, interesting, interfaces. Okay. Remember our ant and bee simulator constructed with unions back in exercises 55 and 56? Yes. Actually, there we demonstrated that unions allow us to treat different data types in a uniform manner. Yes, one neat feature was using tagged unions to create a single function to print a status for ants or bees by switching. Yes. Well, that simulation was running just fine until a new insect arrived in the virtual garden, a grasshopper. Dr. Soraptera started to add grasshopper code to the program, but then she backed away from her keyboard with an angry hissing sound. She had realized that having code for each insect in one place and code for it to print each insect in another place was going to become unpleasant and to maintain when the simulation expanded to hundreds of different insects. Yes, but the compiler does tell you where to put the code, so it's just, I mean, I guess the bad thing is that you have separated the things, like it's fragmented, and it's better probably to have it at the same place. But it's like implementing new ones is actually not that bad, even if you have many. Thankfully, Zig has another comtime feature we can use to get out of this dilemma called the inline else. We can place this redundant code. So we're still using, okay, so we're still using the switch thing. So switch thing special A normal with switch A special inline else normal. Okay, I mean that's very contrived example, because what if everyone is different? Then you still have this problem here. Okay, well, I guess it's nice for this kind of thing. We have special handling of some cases, and then Zig handles the rest of the matches for us. I mean, it's very nice. With this feature, you decide to make an insect union with a single uniform print function. All of the insects can then be responsible for printing themselves. And Dr. Zoroptera can calm down and stop gnawing on the furniture. Yeah, but then you would have this. I mean, you would have like member functions. This is using some kind of function here, like outside, like normal. Where does this come from? You would instead use like t dot and whatever behavior you want to have, like this. I think, yeah. And print and print. So we have two different print things. Very good. Here's the new grasshopper. Also added print methods to each insect. Yes, very cool. Insect. So it's like in Zig, there's no concept of interfaces, but it's kind of like a. I mean, it's not really an interface, but it kind of works like one, sort of. Because you can define this function called print on the union enum, which can be any of these. And then you can switch on self. So you're basically doing a kind of like a, you know, vtable lookup or something. Not really, but you're switching on self. So you're looking at which enum do we have. And then based on that, you would choose a different function based on the enum value. So that's what's happening here. But this is a really nice pattern here. I'm using it a lot in the other code base in the game. For generic code like that. So that's really nice. Thanks to inline else, we can think of this print as being an interface method. Any member of this union, but the thing is though that, I mean, we're not. I mean, we kind of have the signature is sort of in place because, you know, we take nothing, and we have to return a void. So the signature is if you don't adhere to the signature, you're not gonna get like a nice, hey, you're not following the interface error. You're gonna get like this function is just like the return type doesn't match or something like that, which is kind of the same, you know, error type, but it's not like it. I guess it's not like book kept in the compiler the same way and an interface would be, I guess. And also another thing is that you cannot really, I mean, yeah, sure, this is kind of like the interface, but it's also the actual class or whatever you would say, like also like it has both the value and the functions. Okay, well, anyway, my insects. Okay, so we have a couple of insects in a list. Daily insect report. We loop through the insects and we want to print them, so we can just call print. Oh, it returns. No, it returns a void. Okay. Our print method in the insect union above demonstrates something very similar to the object-oriented concept of an abstract data type. That is, the insect type doesn't contain the underlying data. Well, I mean, it does. It's a union enum. What? And the print function doesn't actually do the printing. No. Well, it does it indirectly, I guess. The point of an interface is to support generic programming. I mean, I guess what they're saying is it doesn't contain it directly. I guess it does it indirectly, which is true. The point of the interface is to support generic programming, the ability to treat different things as if they were the same to cut down on clutter and conceptual complexity. A lot of big words. The daily insect report doesn't need to worry about which insects are in the report. They all print the same way via the interface. And Dr. Zoraptora loves it. Cool. Are we done? Okay. Oh man. Hello C. When Andrew Kelly announced the idea of a new programming language named Zig in his blog 2016. Oh wow. So not even 10 years old, this program language. It's very new, you know, relatively to other languages. He also immediately stated his ambitious goal to replace the C language. Yeah, I don't have any opinion on that because I'm not using C normally. In order to be able to achieve this goal at all, Zig should be as compatible as possible with its predecessor. Only if it's possible to exchange individual modules. Yeah, so it's a good strategy because then you can like gradually convert to Zig. If you're using C and then you have projects in C, you can import your other C stuff and like gradually convert. So very cool, very nice. Only if it's possible to exchange individual modules and existing C programs without having to use complicated wrappers, the undertaking has a chance of success. So it is not surprising that calling C functions and vice versa is extremely smooth, quote unquote. To call C functions in Zig, you only need to specify the library that contains said function. For this purpose, there is a built-in function corresponding to the well-known import, C import. All required libraries can now be included in the usual Zig notation. Yes. Now a function can be called via the constant C. C put as hello world. Yeah. So C is kind of now C is like a container for everything that the C. Yeah. I guess runtime or API has, like the C, what would you call it, like everything you could, like if you're making a C program, everything is like available, like if you if you include something that is now globally like available, you don't like yeah, so you don't say like const blah 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 equals import blah blah blah. You just include this. Now you have all the symbols there. All the symbols are imported now implicitly. Now a function can be called via the, in this example, constant C. By the way, most C functions have return values in the form of an integer value. And I think also, you know, I think it's also funny because C is kind of like when you include another file, it basically just copies and pastes that file above your code. I think that's basically what's happening. But it works. Now a function can be called constant C, yes. By the way, most C functions have return values in the form of an integer value. And this is pretty cool because I mean, put s takes a C string, and Zig knows how to like make those and convert into those. So you can put, you know, a literal here, or you can convert other pointers to this type. But it's actually like a C string, I think, if you do it like that. But I think if you do this, you should probably need to add the standard C lib library in order to be able to include standard IO here. I guess they already did that maybe in the build here, but you have, if you're making a new project, I think you have to add the standard library, but it's pretty easy to do. You just say b.add C standard lib or something like that. By the way, most C functions have return values in the form of an integer value. Yeah, so if it's like something, if it's 0, that's not an error, I think. Errors can then be evaluated, returned less than 0, or other information can be obtained. Less than 0. Return less than 0. Wait, okay, so the result is less than 0. For example, put as returns number of characters output. Oh, I see. So if it's like an error, is usually negative. If it returns the number of character output, it's quite positive. Okay, it's kind of a weird way of doing things because it's very shaky. I mean, you have to follow a convention, I guess. So all this does not remain dry theory now. Let's just start and call a C function out of Zig. Our well-known import for Zig, and here's new import. Don't remember what this was. In order to output text that can be evaluated by the Zig builder, we need to write it to the error output. In Zig, we do this with standard debug print, and in C, we can specify a file descriptor EN2 for the error console. Yeah, I mean, yeah, in Linux, right? Or does it work for Windows as well? Like, I don't know. In this, like it's like in the standard library, it would convert it into the Windows version. Because in Windows, you have to call a sys, you have to make a sys call to get the standard out, I'm pretty sure. In this exercise, we will use write to output 17 characters, but something is still missing. Right, I mean, yeah, C dot write. Just write. Okay. Let's see what the result from C is. Okay, so we get I size. Aha. Oh man. I never actually realized that there was a I size version of U size. But okay, yeah, alright. It's kind of like int in C. The int type, which is kind of, it's changed depending on your target architecture. Let's see what the result from C is. C result is the chars written. Something must be considered when compiling with C functions, namely that C compiler knows that it should include corresponding libraries. For this purpose, we call the compiler with this parameter lc for such a program. Link, I guess it means we're linking the the standard C library here. But it still works because you can also do that in build.zig. I think. I mean, it worked now. Oh wait, it's called link, I think. Link. Yeah, here we go. Link libc. Okay, so they defined exercises, and within that definition you can link libc when you're adding that. Okay. So you don't have to worry about that in this exercise. But it's nice that they tell you that. I didn't know that actually, that you could just pass -lc. I think you can also say where's the build, where's the actual build code? Here. So if you have a module somewhere, where are the modules? Here. So you would say zigling. Wait, no, that's a step. First, where are the modules? Well, they're really making a custom build system here, which is one of the very cool things about Zig. Is like the build system also runs in Zig, so you can do a whole bunch of cool things in here and add like preprocessors, or you can do a lot of cool stuff. But you don't want to add too much because it's gonna take more time to compile. So let's see. Here we're so they have like kind of like a little database here. Progress. I see. Compile, no. Step. Oops. I'm just trying to find like a module so I can show. I don't know, maybe link, no, add, where? Here we go, here's a comment, so here we go. Here is, no, that's a run. Well, maybe you can add it here anyway. Let's just create a module, okay? Now we have module. Now we can link libc is true. Okay, I guess you put that to true to make it work. Anyway, that's how you would do it as well. Okay, let's go back. Where was I? Where were we here? 94. Okay, more C stuff. Often C functions are used where no equivalent Zig function exists yet. Okay, that's getting less and less. Okay, I see. Since the integration of C functions is very simple, as already seen last exercise, it naturally offers itself to use the very large variety of C functions for our own programs. As an example, let's say we have a given angle of 765.2 degrees. If we want to normalize that, it means that we have to subtract x times 360 degrees to get the correct angle. But how could we do that? A good method is use the modulo function, but if we write this, it only works with float values that are known at compile time. In Zig, we should use mod instead. Let us now assume we cannot do this in Zig, but only with a C function from the standard library. In the library math, there's a function called fmod, f stands for floating point, or floating, which means that we can solve modulo for real numbers. With this function, not real numbers, floating point numbers, it should be possible to normalize our angle. Let's go. What do we need here? I mean, I guess we need include math. You even get like auto completion here, so that's the amount of C integration you get, which is it's amazing actually. Math dot file not found. Do you just say math, or was it an issue? Do I have to do this? Okay, I think there's some caching issues with the errors here. Okay. Angle is this result c.fmod. So you can even look at this function here. This is pretty cool. So fmod takes x and y, and you know they convert the types and everything. So it's really cool that the C integration is so good that you can look up functions, you can get the types, the signatures, everything here. And I don't think there's any documentation, but is there any documentation in the standard library, by the way? For anything? I would have to look that up sometime. Okay. We use formatters for the desired precision and truncate the decimal place. I'm just gonna look at this. So if you include, let's say you include standard IO, and we call printf. Yeah, so you can see that it's also kind of strange that C can, in order to have the same kind of interface as C, they actually have variadic functions, or variadic number of parameters here, and that doesn't exist in Zig. You can't actually make a function with variadic parameters in Zig. It only exists just to be able to interface with C, which is kind of frustrating actually, because it's a nice thing. I guess. Maybe it's not. I don't know. Maybe it's good. Maybe it's for the better. But here you can see that the type here is *C, which is like a C pointer. So yeah, it's just, but you can put anything, like anything in here, and it will still work. And yeah, like normal. So that's really cool. I just think that's so good that it can do that. We use formatters for desired precision, truncate decimal places. Normalized angle is blah blah blah. Okay, did we? Yeah, great. Okay, now we're on to for loops again. So only 5 left. The Zig language's rapid development continuously improves the language construct. Ziglings evolves with it. Yes, which is very nice, because otherwise it would be stale and not used. So I really like that they are doing this. Until version 0.11, Zig's for loops did not directly replicate the functionality of the C style, which are so well suited for iterating over a numeric sequence. Instead, while loops with counters clumsily stood in their place. Yeah, so you could do this to mimic the old style for loops, but you can also do this, which is kind of the same thing, but in a more terse format. So you're kind of defining a range from 0 to 10, but I will never be 10 here, so it's kind of like, I is equal to 0, I is less than 10, and I plus plus is like implicit, and then you can capture out you can determine what the name should be for this variable. So this is a really nice thing here. Okay, so this was actually added in 0.11. Cool. All right. The key to understand this example is to know that 0 to 9 uses a new range syntax. Yeah. At the moment, I mean, didn't that exist in slices? When you're slicing, you use the same syntax. At the moment, ranges in loops are only supported in for loops. Okay, so you can't like do it in a while loop, or I mean that would be kind of the same thing, right? Perhaps you recall exercise 13. We were printing a numeric sequence like so. N U32 equals 1. I want to print every number between 1 to 20 that is not divisible by 3 or 5. Yes. Modular operator, continue, yes. Let's try the new form of for loops to re-implement the exercise. Oh, I see, so this is like an updated version of Zig. Brings us more for exercises, okay. So this would be between 1 and 20. So we start at 1. And between, or do we start at 2 then, because it's between? No, I'm gonna assume that it starts at 1 and it doesn't include 20. Yeah, I don't know. We'll see. There's a module, yes, then it's the same thing. That's a bit nicer, right? Of course, both while and for have different advantages. Exercises. Maybe this is why I've never seen the continuation expression from while, because this is how you would do it probably now instead. Except that the continuation expression in while has more versatility. So as long as you only wanna, but it's very good to know, because then you can increase by whatever you want. This is like super good for if you just increase by 1. Of course, both while and for have different advantages. Exercises 11, 12, and 14 would not be simplified by switching a while for a for. Right. Okay. Well, it depends. I mean, if they introduce something like, I don't know, +2, I don't know, some other syntax, like 1. I think some languages have like, if you start like this, you know that it should start at 1 and then add 1 to get to 2 and then up to 20. But if you say 3, it means add 2 and then up to 20. You know, you could introduce something like that, but I guess maybe. There we go. 96. Memory allocation. Okay, wow. Finally, we get to this part. In most of the examples so far, the inputs are known at compile time. Thus, the amount of memory used by the program is fixed. However, if responding to inputs whose size is not known at compile time, such as user inputs via command line arguments or inputs from another program, you'll need to request memory for your program to be allocated by your operating system at runtime. Zig provides several different allocators. In the Zig documentation, it recommends the arena allocator for simple programs which allocate once and then exit. Yes. So you have one. Yeah, memory allocation can fail, which is annoying. So there's an error type in there every time you allocate something. Arena, because the memory can run out. That's the error that you can get. But if it runs out, then you basically can't do anything either. So, but anyway, so if you have you can have an arena allocator here, and deinitialize it at the end, which will release everything that has ever been allocated with this allocator. And here's how you create the allocator from this arena. And then we create some I32 here on the stack. Actually, this is the page allocator. So this is you need a backing allocator for the arena allocator. So this uses the built-in like page allocator, which always, I think in the documentation it says that it always does a syscall for all allocations. And then we have a pointer that we create to hold an I32, so that's created on the heap. We will print that out because you get a pointer to where you can store the data, and then we allocate a 5 length array with F64, so you can, and you get a slice pointer from that, which is very nice. And then we can print that out. Instead of a simple integer or slice with constant size, this program requires allocating a slice that is the same size as an input array. Given a series of numbers, take the running average. In other words, each item n should contain the average of the last n elements. Each item n should contain the average of the n last elements. So the first, so 0 should contain, or the first one should contain itself. 2 should contain average of 1 and 2. 3 should contain average of 1, 2, 3. Okay. Okay, well, they're doing kind of this, so running average. So we get a constant slice of array, and then an average slice, which is mutable. So I guess we're supposed to mutate every, we're calling this function one time to populate average, I guess. And so we have a running total. We're going through each array element. We get the index. I'm gonna rename that right now. And we get the value. Okay. So we're increasing the sum. We are getting a float index. Okay, so that's how many items we have. Index 0, so it's, yeah, so that's 1, right? And then average I equals a sum over that. I mean, I don't need to fix anything here, I don't think. Main, pretend this was defined by reading in user input. Okay, we're pretending. I was thinking like we could make this so that it actually does that, but I'm gonna go ahead and not do that. Initialize the allocator, arena allocator. We get an arena allocator, we defer it, we get the allocator, and here we need to, okay, so here's what we need to do. So we will use allocator and we will allocate, and what do we allocate? We allocate F64s, and how many? Well, it's gonna be the length of this array. There we go. And we call this to populate it and we print it out. For more details on memory allocation, different types of memory allocators, see this video. Okay. I may watch that later. So no. Oh, I see. Yeah, this could be an error, so we have to do try on that. There we go. Now that's the running average. I'm just gonna assume it's correct. We passed the test. All right, bit manipulation. Okay. Bit manipulation is a very powerful tool, also from Zig. Since the dawn of the computer age, numerous algorithms have been developed to solve tasks solely by moving, setting, or logically combining bits. And it's, I mean, it's not usually a problem that I tend to solve, like using bit manipulation, because it's like, it feels like you have to spend a lot of time to find something that is like a confusing solution to something else. I don't know. Zig also uses direct bit manipulation in its standard library for functions where possible, and it's often possible calculations based on integers. Okay. At first glance, it is often not easy to understand what exactly these algorithms do when only numbers in memory areas change outwardly. Yes, that's true. However, it should never be forgotten that the numbers only represent the interpretation of the bit sequences. Yeah. Quasi, the reversed case we have otherwise, namely that we represent numbers in bit sequences. Everything is bit sequences in the computer. We remember 1 byte equals 8 bits equals that. Yes, we provide all necessary functions to change the bits inside a variable. It is distinguished whether the bit change leads to an overflow or not. The details are in the Zig documentation in the table of operators. Here are some examples of how the bits in variables can be changed. Okay, so we're just assigning a number here, yeah. And here we're doing bit shift, so shift right 4 times, shift left 4 times. Also the same as taking or multiplying by 2 to the power of x, where x is 4, I believe, 4 times. We're multiplying by 2 4 times. I'm pretty sure that's what's happening. And then we have this, and it's a very fast operation as well. And then let's see, AND or XOR. To familiarize ourselves with bit manipulation, we start with simple but often underestimated function and then add other exercises in loose order. The following contains excerpt from Wikipedia. Swap. In computer programming, the act of swapping 2 variables refers to mutually exchanging the values of the variables. Usually this is done with data in memory. For example, the program 2 variables may be defined. Data item x, y, swap x, y. You have to have a temporary variable to store one of the things because you're overriding the destination when you're assigning the value. X will contain the value 0, y will contain 1, values have been exchanged. The simplest and probably most widely used method swap is the third temporary variable. However, with integers, we can also achieve the swap function simply by bit manipulation. To do this, variables are mutually linked with XOR, and the result is the same. Does that work for all values? I mean, I guess, maybe. Let us use this as values for x and y. Now we swap. But okay, so first we're XORing x by y, So x has now been changed into y, I presume, because we're not doing anything else with x. This doesn't make sense. No, but then y is XOR by itself in that case, which would result in a bunch, well, actually, what would that result in? A bunch of zeros, right? I don't understand. Okay, so let's see, what would x be after, what will x be after this? 0, 1, 1, 0, right? That's not y. And then now y here will be 1, 1, 0, 1, which is x. Okay. But then what do we do with x? One, zero, zero, no. 1, 0, 1, 1. Oh, so we just do this again. Wow, I actually didn't know this. This is pretty cool. So this would now be 1, 0, 1, 1, which is y. Oh. Okay, that's actually pretty nice. If you ever wanted to do that, because I never have that situation, but the variable swap takes advantage of the fact that the value resulting from the XOR of two values contains both of these values. The circumstance was and still is sometimes used for encryption. I mean, it's pretty magical, to be honest. It's kind of, it's like encoding both values in one thing. It's kind of like creating a key. Yeah. That's pretty cool. Value XOR key. Yeah, I've never went so much into crypto, so that's why I'm kind of astonished by this. Because this would be like basic knowledge probably. Since this can be swapped arbitrarily, you can swap two variables in this way. Or crypto, not crypto like crypto, but cryptography, encryption. You can swap two variables there. Yeah, I didn't know that. That's actually pretty cool. Crypto is better not to use this, but in sorting algorithms like bubble sort, it works very well. Okay, yeah, okay. So you're not using it, and still is sometimes used for encryption. Okay, but I mean, I guess it proves it's like it could be used for demonstration purposes. All right, bit manipulation 2. Another useful application for bit manipulation is setting bits as flags. This is yeah. I'm pretty. I know this prime flag list of numbers, and for each prime number, a flag is set. Okay. As an example, let's take a pangram exercise from Exorcism. Exorcism. I've never heard of that. That could be cool. Let me just... No. 1 second. Exorcism. I see, you have to like log in. Okay, anyway. A pangram is a sentence using every letter of the alphabet at least once. Oh. In this case, insensitive. It is case insensitive. So it doesn't use... Man, I can't read. So it doesn't matter if a letter is lowercase or uppercase. The best known English pangram is the quick brown fox jumps over the lazy dog. Yes, that's amazing. There are several ways to select the letters that appear in the pangram, and it doesn't matter if they appear once or several times. Is every letter appearing once or twice here? The appears twice. For example, you could take an array of bool and set the value to true for each letter in the order of the alphabet found in the sentence. However, this is neither memory efficient nor particularly fast. Instead, we choose a simple approach that is very similar to the principle. We define a variable with at least 26 bits and set the bit for each letter that was found in the corresponding position. Zig provides functions for this in the standard library, but we prefer to solve it without these extras. What kind of functions? After all, we want to learn something. Wait, which functions are you talking about? Okay. Let's check the pangram. Is this a pangram? Is pangram. Okay. Wait, what's this? ASCII? I've never seen this. Library. Interesting. Is pangram. First we check if the string has at least 26 characters. Yeah, I guess that's a good first check. We use the 32-bit variable, which is we need of which we need 26 bits. I mean, couldn't you do this? You could do this, right? Maybe there's a reason why you don't. Loop about all characters in the string. Loop about. Okay, we're going through each character. If the character is an alphabetical order, if the character is an alphabetical character. Oh, is that what it's used for? Well, how are you learning now? We're using standard library here. Is ASCII. So what do you do? C is less than 128. That was pretty simple. Is alphabetic more than or equal to lower? Is it lowercase or uppercase as the first one? I think it's lowercase. Okay, well, you have to do greater than or equal to lowercase a, less than or equal to lowercase z, and then the same for uppercase a and z. But maybe there's a more efficient way. Or not, maybe. Then we set the bit at the position. To do this, we use a little trick. Since the letters in the ASCII table start at 65 and the numbers sequentially, we simply subtract the first letter, in this case the lowercase a, from the character found, and thus get the position of the desired bit. Yeah, if we're only dealing with like lowercase, this should suffice, and no other strange characters. Because you can get in here with uppercase, that will not work. Last, we return the comparison if all 26 bits are set, and if so, we know the given string is a pangram, but what do we have to compare? Bits equal to... It's a 26. No, it's 32. Okay, so I guess it's easier to define. you put this. Everything should be on. No, wait, it should be 26. Is it lower? Is it the first one? $26 bits. It's easier to do this. One, two, three, four. 12, 16, 20, 24, 26. Is that correct? Yes. Okay, cool. I'm not sure how to, like, for hex. I mean, this would become, so this is F, 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 and I guess this would be 3. Well, I got past it, so I won't check it again, so. Okay, let's continue. Formatting. Terminals have come a long way over the years, starting with monochrome lines on flickering CRT monitors and continuously improving to today's modern terminal emulators with sharp images, true color fonts, languages, and characters in every known language. Thank God we are, or thank someone we are where we are. Formatting our results to be appealing and allow quick visual comprehension of the information, that is what users desire. C set string formatting standards over the years, and Zig is following suit and growing daily. Due to this growth, there is no official documentation for the standard library features such as string formatting. Therefore, the comments of the format function are the only way to definitely learn how to format strings in Zig. Yeah, you have standard. No, where is it? Print. Is it format? Is this one? No. Oh, deprecating. Where is this? Where's the documentation? Whoops. Wait, writer, no, IO, writer, print. Here we go, here it is, okay. Yeah. So is this the same as in, I have a hard time thinking that this would be the same as in, I mean, I know that X is for hex. but yeah. Anyway, as in C. Zig is already a very nice selection of formatting options. These can be used in different ways, but generally to convert numerical values into various text representations. The result can be used for direct output to a terminal or stored for later use or written to a file. The latter is useful when large amounts of data are processed by other programs. I actually really like, you know, the streaming stuff that Zig does right now. Like, I don't know. I just think it's pretty cool, the writer and reader things and how it's like incorporated into the standard library. In Ziglings, we are concerned with the output to console. I'm gonna guess it could change with the async await update. We'll see how things will go. I don't know what's gonna happen, but we'll see. In Ziglings, we are concerned with the output to the console, but since the formatting instructions for files are the same, what you learned applies universally. Yeah. Since we write to debug output in Ziglings, our answers usually look something like this: print text, placeholder, another text, and then foo. In addition to being replaced with foo in this example, the placeholder in the string can also have a formatting applied. How does that work? This actually happens in several stages. In one stage, the escape sequences are evaluated. The one we've seen most is /n, which means line feed. Whenever this statement is found, new line is started in the output. The escape sequences can also be written one after the other. Yes. By the way, the result of this escape is passed directly to the terminal program. I'm translating. Nothing to do with Zig. Zig knows nothing about line feeds or tabs or bells. Okay, yeah. Well, they have to. Zig has to take /n and turn it into the proper ASCII value, and then put it there. But other than that, it's just a number. It has to be like a map from the escape sequence to the actual ASCII value. I mean, the same goes for, you know, strings with you know, alphabetical numbers and everything. Here has to be mapped. Okay, anyway, the formatting that Zig does perform itself is found in the curly brackets. Placeholder. Formatting instructions in the placeholder will determine how the corresponding value was displayed. Yes, and this is where it gets exciting, because format accepts a variety of formatting instructions. It's basically a tiny language of its own. Here is a numeric example. I mean, we've been through this a little bit, so this would be like hexadecimal and 0 padded, align right, 4 width. Yeah. So you could format, for example, like, well, this would be a 16-bit number. We can center a line. Oh, center a line. But I guess I would learn this if I go ahead and read everything in the formatting documentation, but yeah. Let's see. So we got the format. Let's add align center. But this one is 20. So I guess this would be the width as well. What about the star? I guess you have to say store. Maybe. I wonder if you could pad it with 0 and it would pad like both left and right or something. Align center. Okay. Output. Oh, okay. I should have looked here. So it's like padding with star. So this is okay. So padding with star. I see. That's pretty cool. Let's try making use of some formatting. We've decided that the one thing missing from our lives is a multiplication table for all numbers 1 to 15. We want the table to be nice and neat with numbers in straight columns like so. Alright. Without string formatting, this would be a more challenging assignment because the number of digits in the numbers varies from 1 to 3. But formatting can help us with that. That's cool. Okay, so max number to multiply 15, print the header. Start with a single X for the diagonal. Header row with all numbers from 1 to size. So here we are aligning with width 3. So what, so, okay. And then a space in between, I guess. Yeah, here is the space. And an end line, and then the column line. We are doing this. I think you can also do, couldn't you do this as well? Maybe? I guess we'll see. If it, because now it's like this, just this every time. Now the actual table. Also this, okay, they were using a while loop down here. Here's like the for loop that I was gonna change it into, but then I realized, well, you can use this maybe. Okay. Now the actual table. Is there anything more beautiful than a well-formatted table? 0 to size A, D, line to A plus 1, align 2, okay. How did it look here? So this is the first one, okay. And then, so that's the okay, that's the first thing. And then we go to a nested loop, and here we need 3 number, decimal number 3 wide, and yeah. Wait, what's the issue? I see, we're missing one one of these. Should have one more. But it did work. So size plus 1. Okay. Yeah, it worked. Cool. Now we're 100. So only, I think there's only like 10 left. 110 is the last one. Okay, we've seen that the for loop can let us perform some action. for every item in an array of slice. More recently, we discovered the support ranges to iterate over number sequences. This is part of the more general capability of the for loop, looping over one or more objects where an object is an array, slice, or range. Okay, there's a weird way of putting it, because I would think of an object as the elements in the array, slice, or range. Okay. In fact, we did use multiple objects way back in exercise 16, where we iterated over an array and also a numeric index. It didn't always work exactly this way, so the exercise had to be retroactively modified a little bit. Alright, the general form of a for loop with two lists is this. Yeah, this is kind of weird. Like, I actually never really used this way of doing it. I usually, when I have this problem, I usually just make an index and access the elements directly instead of doing this, because it just feels strange. Like, it's kind of like the zip from a functional program where you're zipping two lists. And it's like, okay, so I guess it's gonna pick the short. What if one list is shorter than the other one? I guess it's gonna pick like the shortest one, or I don't know how it works. Maybe we'll learn here. Here we have the first item from list A and list B, then the second item from each, and the third, and so forth. What's really beautiful about this is that we don't have to keep track of an index of the balancing memory pointer for either of these lists. That error-prone stuff is all taken care of. Yeah. Below, we have a program that is supposed to compare two arrays. Please make it work. So we got two things. I mean, arrays match. Woohoo! You're perhaps wondering what happens if one or two lists is longer than the other. Try it. By the way, congratulations for making it. Okay, let's try it. Let's make this. Let's add 13. Okay, and yeah, it won't work, so erase my. Okay, well now they are different, so if I do this, what does this, is it? Oh, it's a compiler error, I think. Non-matching for loop lengths. I see. Okay, so I never seen this. Okay. Good to know, I guess. 101. 4, 5. The for loop is not just limited to looping over one or two items. Let's try an example with a whole bunch. But first, there's one last thing we avoided mentioning until now. The special range that leaves off the last value for things. Special range that leaves off the last value. Okay, yeah, so yeah, this would be 0 to the length of things. So it's just a very convenient way of, if you need both the item and the index, you can do this as a kind of like a shorthand. That's how we tell Zig that we want to get the numeric value for every item in things starting with 0. Otherwise known as the index. A nice feature of these index ranges is that you can have them start with any number you choose. The first value of I in this example will be 500, then 501, 502, etc. Right. Remember our RPG characters. They have the following properties, which we stored in a struct type. Class gold experience. What we're going to do now is to store the same RPG character data, but in separate array for each property. It might look a little awkward, but let's bear with it. Okay, we started writing a program to print a numbered list of characters with each of the properties, but it needs a little help. This is the same character roles we've seen before. Okay, here are the 3 property arrays. Property. We would like to number our list starting with 0, with 1, not 0. How do we do that? There we go. And great. By the way, storing our character data in arrays like this isn't just a silly way of demonstrating multi-object for loops. It's also a silly way to introduce a concept called data-oriented design. Let's use a metaphor to build up an intuition of what it's all about. I believe there's also, like, if you have this, there's a built-in function. There's like a built-in. But let's say you have a struct RPG char original or something, and you have a role, you have gold and experience, and now if you want this type of, you know, structure, you can instead say what is it, multi-array list. So now this yeah, the multi-array list will turn, it says here, stores a list of struct or tagged unit type. Instead of storing a single list of items, multi-array stores separate lists for each field of the struct and lists of tags and values. So yeah, so now you basically have a struct with lists here instead. And actually this is a list. Actually this is like RPG char list, and this is, I guess this is the RPG char, and then you can say chars equals to RPG char list empty, and then we'll chars append. Wait, can't you append a slice on this version here? Okay, I guess you have to, well, we need like an allocator. Let's just use page allocator, and then we have a char roles a wizard, golds 25, experience 40. Let's just make this as an example. So we append this, and I think now we get the, we can get the, yeah, we get the item, we get the 0th char character, not char, or car. How do you pronounce it? I say char. Okay, anyway, so you get the 0. Now it's stored as a struct with arrays, like this is like stored as one struct like this, but with these as arrays. But you do get, when you call this, you will get this type out. So that's what's nice to do it. And why would you do it? Well, there's like memory and CPU cache reasons to do it. Like it could be faster in some cases to do it like this. Okay, but I mean, it's kind of like we're doing it manually here, but I just wanted to show that because that's kind of the same thing, except it's like a built-in array list that you can use for that. Situated data design. Let's say you did been tasked with grabbing 3 glass marbles, 3 spoons of 3 feathers from a magic bag, but you can't use your hands to grab them. Instead, you must use a marble scoop, spoon magic, and feather tongs to grab each type of object. So you can only grab one type at a time. Now, would you rather use magic bag grouped the items in clusters, so you have to pick up 1 marble, then 1 spoon, then 1 feather, or group the entire by type, the items by type, pick up all the marbles at once, all the spoons, all the feathers. Yeah, so B is way faster. If this metaphor is working, hopefully it's clear that B option would be much more efficient. Well, it probably comes as a little surprise that storing and using data in sequential and uniform fashion is always so more efficient for modern CPUs. Because of tips and tricks. They're using tricks. Yeah, 101 already. There's only 9 left now. It goes up to 110. Decades of OP practices steer people towards grouping different data types together with mixed type objects with the intent that these are easier on the human mind. Data-oriented design group data groups data by type in a way that is easier on the computer. With clever language design, maybe we can have both. Yeah, so that's the thing also. Like the multi-array list is a really nice way of storing the data in this way, but then to the user, you see each item as just the normal struct. So it's a really nice way of fixing that issue. But then I think in Odin, I think I heard that they store the arrays or whatever they have, like as structure of arrays always. Like if you define, like they optimize that for you, so you don't really have to like program it like array of structs, but they will turn it into an array of structs. And or no, I'm sorry, a struct of arrays. They will turn array of structs into a struct of arrays and then optimize that automatically. I'm pretty sure I've heard that somewhere. Which is also a nice way of doing it, because then you really don't need to think about it. With clever language design, in the C community, we may see the difference in groupings presented with the terms array of structs versus structs of arrays. To envision these two design in action, imagine an array of RPG character structs, each containing 3 different data types, versus single RPG character struct containing these 3 arrays of data type, each like those in the exercise above. For a more practical application of data-oriented design, watch the following talk from Andrew Kelly, creator of Zig. Alright. Now we're on to 1, 2, 3. Testing. Okay. Big advantage of Zig is the integration with its own test system. Yes, the test system is very nice. This allows the philosophy of the test-driven development to be implemented perfectly. Zig goes even one step further, and other languages tests can be included directly in the source file. This has several advantages. I mean, there's even, yeah, there is even like special syntax for tests, so it's really nice. This has several advantages. One hand, is much clearer to have everything in one file, both source code and associated test code. On the other hand, it's much easier for third parties to understand what the function is supposed to do if they can simply look at the tests inside the source code and compare both. It's also a nice, because you have a place to put your test, which usually could be, you know, a source of friction when actually implementing a project. Like, where should I put the test? Like, I should have like a special folder called tests, and I have to match on the files, on the file names to run these tests and all that. You just skip all that and just put the test directly in the code. And it's also like, you can just directly look at your function to write the test as well. It's very nice. Yeah, especially if you want to understand how the standard library of Zig works. This approach is very helpful. Furthermore, it's very practical if you want to report a bug to the Zig community, illustrate it with a small example including a test. Therefore, in this exercise, we will deal with the basics of testing a Zig. Basically, test works as follows. You pass certain parameters to function for which you get a return result. This is then compared with the expected value. Both values match. Tests passed, otherwise the message is displayed. Yes, I know all this. I'm skipping. I'm just skimming through here. Also, other comparison of possible deviations or also errors can be provoked, which must lead to problems and best. Tests can be run via the Zig build system or applied directly in video wells. Okay, I didn't know you could do this, but I mean, it makes sense. You could just say Zig test, I think, and it will test everything. Both can be used script driven to execute tests automatically after checking into a Git repository. Something we can also make extensive use of here. That's ziglings. Great. Okay, we got an add function, we got a test, We're expecting to get some results here. This should all be fine, except this, yeah, it's floating point, so that should be fine. Another simple function returns test subtraction. Okay, we're testing that. Aha! An error in the test. Okay, this. And if there's an error, it will be reported. Oops. What the hell is happening there? Yeah, okay. And then we also have some thing here. Expected error. Division by 0, maybe? Okay. Right, yeah, you expect an error. Yeah, and here's a failing test. Yeah. So this one failed, so we fix that. Okay, great. Tokenization. Functionality of standard library is becoming increasingly important in Zig. First of all, it's helpful to take a look at how the individual functions are implemented, because this is wonderfully suitable as a template for your own functions. In addition, this standard function is part of the basic configuration of Zig. This means they're always available in every system, therefore it's worthwhile to deal with them also in ziglings. It's a great way to learn important skills. For example, it is often necessary to process large amounts of data from files. For this sequential reading and processing, Zig provides some useful functions, which we will take a closer look at in the coming exercises. A nice example of this is that has been published on the Zig homepage, replacing the somewhat dusty Hello World. Nothing against Hello World, but it just doesn't do justice to the elegance of Zig, and it's a pity if someone takes a short first look at the homepage and doesn't get enchanted. And for that, the present example is simply better suited, and will therefore use it as an introduction to tokenizing, because it is wonderfully suited to understand the basic principles. In the following exercises, I mean, to be honest, I don't think the Hello World example is like it. I mean, it doesn't really. It's probably doesn't show what would be nice about Zig. It just shows, you know, the standard. You have a public main function and you call a print function. You actually, it's actually more complicated because you have to get the standard out writer now, and then say writer.interface.print. But yeah, and it doesn't. It shows that it's like printing is like complicated. But yeah, it's yeah, it's like one step more than probably most, like all other programming languages. But I don't mind. But it is nice because you get a writer out, which is good, and it doesn't really show the, you know, what could be nice about the language. So I agree with that. In the following exercise, we'll also read and process data from large files and the latest. 1 second here. Latest, then it will be clear to everyone how useful all this is. Let's start with the analysis of the program on the Zig homepage and explain the most important things. So const standard, yes, we import that. Here's a function on the standard line defined. So parse int, yeah, it takes a string and gives you an integer. Okay, so we have a test already. Defining a test case. 4 numbers are passed into a string. Please note that the individual values are separated either by a space or a comma. In order to be able to process the input values, memory is required. An allocator is defined here for this purpose. Ally, standard testing allocator, okay. The allocator is used to initialize an array into which the number are stored. Yeah, so this is the first time we're seeing like an array list here. but I mean, yeah, it's just a struct with a bunch of convenient functions for managing an array that is like managed by an allocator. When I say, yeah, this is like, okay, well, you can append things into it using an allocator. You can change the size of, you can of the list. You can set the capacity. Yeah, it's just, if you want a dynamic sort of list, this is the way to go. You can also use array hash map, like string array hash map. No, wait. Array. No, yeah, but that is for hash maps. But it's also stored as an array, so you can like loop through it. This way you can never forget what is urgently needed. The compiler doesn't grumble either. The allocator is used to initialize an array into which numbers are stored. Yeah, and we defer the initialization after that because it's coupled with this list, with the initialization and the initialization. It's really nice that you can put it at the same place, but it's not executed at the same time. Now it gets exciting. A standard tokenizer is called Zig has several and used to locate the positions of respective separators. Remember space and comma and pass them to the iterator. Yeah, this is pretty cool. And I should probably maybe like rewrite the example we did earlier using these because it's pretty cool. The iterator can now be processed in the loop and the individual numbers can be transferred. Yeah, so we're using an iterator. We're doing while iterator.next, which returns a optional value, which you can then capture match here, and if it's null, it's gonna exit the while loop. If it has a value, it will iterate here. But be careful, the numbers are still only available as strings. This is where integer parser comes into play, converting them into real integer values. Yes. Finally, and I guess this is the radix. Finally, the individual or base, the number base, what's it called? Whatever. Finally, the individual values are stored in the array. Yes. For the subsequent test, a second static array is created, which is directly filled with expected values. Yes, these are expected. Okay. Now that numbers are converted from the string can be compared with the expected ones that the test is completed. Yes, and I believe there's also like a expect sequence or slice or something. There you can match like two lists. I mean, you could do this as well, but yeah. You get more information, I guess, if you're using testing.expect sequence or something like that. So much for the example from the homepage. Let's summarize the basic steps again. We have a set of data in sequential order separated from each other by means of various characters. For further processing, for example, in an array, this data must be read in, separated, and, if necessary, converted into target format. We need a buffer that is large enough to hold the data. This buffer can be created either statically at compile time, or the amount of data is already known, or if the amount is already known, or dynamically at runtime by using a memory allocator. The data is divided by means of tokenizer at the respective separators and stored in the reserved memory. This usually also includes conversion to the target format. Now the data can be conveniently processed further in the correct format. These steps are basically the same always. Whether the data is read from a file or entered by the user via the keyboard, for example, is irrelevant. Only subtleties are distinguished, and that's why Zig has different tokenizers. But more of this in later exercises. Now we also want to write a small program to tokenize some data. Alright, I'm getting a call there. Wait a minute. All right, I'm back. Alright, now we also want to write a small program to tokenize some data after. Oh, we need some practice. Suppose we count the words of this little poem. My name is Ozymandias, King of Kings. Look on my works, ye mighty and despair. By Percy something something. Okay, so here's the input. So we have a bunch of different delimiters, space, comma, and semicolon, new line, and I guess exclamation mark maybe. What do we need to hear? Okay, so let's just put them here. Print all the words and count them. This little poem has this many words. Alright, let's see if that works. Yes, it passed. Great. Oh, threading. This is actually something that I've never done in Zig. Alright, 6 left, come on. Whenever there's a lot to calculate, the question arises as how the task be carried out simultaneously. We have already learned about one possibility, namely asynchronous processes in exercise. Well, we haven't because it's not implemented. However, the computing power. So I don't know if that's gonna come in Cirpos like the next major version, or if we have to wait one more. But it feels like it should come after. I think they're working on like a lot of compiler stuff now. Like, I mean, obviously the compiler, but they're working on like the backend to move from LLVM. I think that's what they're focusing on right now, if I'm not mistaken. And I think async will come like after that. I'm not sure, but that's the feeling I've got. I guess you can look in the homepage to see maybe what the plan is. We've already learned about the one possibility now. However, the computer powered process is only distributed to the started and running task, which always reaches its limit when pure computer power is called up. Wait, what's the? However, the computing power of the processor is only distributed to the started and running tasks, which always reaches its limits when pure computing power is called up. I don't understand this sentence here. Which always reaches its limit when pure computing power is called up. Okay, we'll just skip this. For example, in blockchains based on proof of work, the miners have to find a nonce for a certain character string so that the first m bits in the hash of the character string has character string and the nonce are zeros. As the miner who can solve the task first receives the reward, everyone tries to complete the calculations as quickly as possible. This is where multi-threading comes into play, where tasks are actually distributed across several cores of the CPU or GPU, which then really means multiplication of performance. The following diagram roughly illustrates the difference between the various types of process execution. The overall time column is intended to illustrate how the time is affected if, instead of one core as in synchronous or asynchronous processing, a second core now helps to complete the work in multi-threading. In the ideal case shown, execution takes only half the time compared to the synchronous single thread, and even asynchronous processing is only slightly faster in comparison. Synchronous, asynchronous processing versus multi-threading. blocking. Task 1. Task 2. Well, where is this run then? Like the asynchronous. Task 1, task 2. So task 1 is done over here, and then task 2 down there. But what? And this one does more. But what? How does this work? What's happening here? The diagrams modeled on the one in a blog in which the differences between asynchronous processing and multi-threading are explained in detail. Okay, I guess I'll have to read that. Our exercise is essentially about clarifying the approach in Zig, and therefore we try to keep it as simple as possible. Multi-threading yourself. I mean, okay, I guess, you know, there's a thing called like threads, but it's not necessarily run on separate cores. Like this is separate cores, but if you only run on separate threads but on the same core, then you still run it like you're still sharing the same. I mean, it's just like process, like having multiple processes running at the same time. Let's say on one core, you're still sharing the computer power. It's just that it takes, if you have one process, it takes X amount of time. But if you have two processes, it takes like two of the same process. It takes now. It takes half, or it takes X times 2 time to complete both processes if they are completed within the exact same time every time you run the program. Let's say a program takes 1 second to run. If you run it on one program on one core only, it will complete in 1 second. If you run 2 programs on one core, it will take 2 seconds to complete them. But they are kind of running in parallel, but they, you know, they're sharing the computer. Actually, it will take longer because you have like context switching and stuff happening. Our exercise is essentially about clarifying the process. This is where preparatory work takes place before a parallel starting work. These curly brackets are very important. See, they are necessary. 2. Enclose the area where the threads are called. I see. Yeah, for the defers. Without these brackets, program would not wait for the end of the threads, and they would continue to run beyond the end of the program. Really? Oh yeah, because of the defer. We're deferring the join, so that would happen over here. But that would happen over here as well, right? If you're deferring the join to the end of the... Or maybe... Without these breaks, the program will not wait for the end of the threads, and they will continue to run beyond the end of the program. Okay, whatever. Now we start the first thread with a number as parameter. So we call standard thread spawn. That spawns a new thread. Then you can supply config stuff here. Allocator, stack size, okay. I thought, couldn't you... And then you have a handle. Do you have any... Okay, so you can like call stuff on this handle. You can detach, which I think has different meanings depending on your operating system, maybe. Okay, well anyway. So we spawn a new thread and then you pass a function that is the main function of that thread, sort of. So this function will be ran in a thread, and you can also pass an argument, I guess, to it. Okay. How does this work? Like, is this checked in runtime, or I mean in compile time, like the arguments, because it is compile time known, the function and the type of args. Okay, I guess since we're like, oh, we got implementation. Unsupported. What is this for different? Yeah, Windows thread. Okay. Different operating systems. And where are we calling this function here? Wait. Any type? Oh, I see. Okay, we're creating a new. Okay. So this is kind of how you can get an any type into a struct, but not really. Okay. Anyway, so we create this thing. Okay, we're waiting for the thread to complete, and the allocation and the resources created on spawn. Okay, second thread. Yeah, okay, we're creating. So what does this actually do here? We're sleeping. And this is unsigned. Yeah. Thread. Okay, so it's just sleeping and then simulating some work here. Now this would be a compiler error, because this should be okay. Third thread. I guess we can do this to see what happens. Handle 3, defer, join. After the threads have been started, they run in parallel, and we can still do some work in between with the main thread. But we're sleeping, and then somewhere stuff after starting the threads. Okay. After we have left the closed area, we wait until the threads have run through. If this has not yet been the case, so this is kind of like a async await here, because we're spawning. This is like an async call to thread function. Or async call. I mean, yeah, we're calling thread function asynchronously, and then this over here, and then at the end, these joins are like await, kind of. After we have left the closed area, we wait until the threads. All right. This is the easiest way to run threads in parallel. In general, however, more management effort is required, setting up a pool or allowing threads to communicate with each other using semaphores. But that's a topic for another exercise. Okay. Well, there's not much exercises left, so we'll see what happens. Okay, so we fixed that. Now this should be like a. Will this be a compiler error up here? Or will it be a runtime error? Because no, it should be, must have been, it must be a compiler error. Cannot represent, yeah. But kind of bad error though. F reference trace. Sig build reference trace F reference trace. Okay, maybe it's a separate build thing that I can't pass things to. Okay. Yeah, okay, so -4, we change you to 4. Okay, thread 1 started, 3 started, 4 started, 1 finished, 4 finished, 3 finished. And wait, what? Where's thread 2? Oh, okay, so this is thread 2. So 1, 2, 3. Oh. I see. This could be the start of making the game, like making the physics engine maybe multi-threaded, perhaps. Maybe. Compiling, checking. Expected type, now we're on the next one, right? Threading 2. Now that we're familiar with the principles of multi-threading, well, let's boldly venture into a practical example from mathematics. We will determine the circle number pi with sufficient accuracy. There are different methods for this, and some of them are several hundred years old. For us, the dusty procedures are surprisingly well suited to our exercise, because the mathematicians of the time didn't have fancy computers which we can calculate something like this in seconds today. Whereby, of course, it depends on the accuracy, how many digits after the decimal point we are interested in. But these these old procedures can still be tackled with paper and pencil, which is why they're easier for us to understand, at least for me. So let's take a mental leap back for a few years, around 1672. If you want to know and read about it in detail, you can do so on Wikipedia, for example. Various mathematicians once again discovered a method for approaching the circle number pi. There were Scottish mathematician Gregory and a German Leibniz, and even a few hundred years earlier, the Indian mathematician okay, I'm not gonna pronounce that, Madhava. All of them independently developed the same formula, which was published by Leibniz in 1682 in the journal Acta Eruditorum. Okay. This is why this method has been known as the Leibniz series, although the other names are often used today. We will not go into the formula and its derivation in detail, but we will deal with the series straight away. So pi equals 4 of 1 minus 4 of 3 plus 4. So it's 4 over n, where n is odd. All the odd numbers start from 1 going up and then alternating negative and plus. Cool. As you can clearly see, the series started with a whole number 4 and approaches the circle by subtracting and adding smaller and smaller parts of 4. Pretty much everyone has learned that pi equals 3.14 at school, but very few people remember other digits, and this is rarely necessary in practice, because either you don't need a precision or you need to use a calculator in which the number is stored and a very precise constant. But at some point this constant was calculated, and we are doing the same now. The question at this point is, how many partial values do we need to calculate for which accuracy? The answer is chewing. To get 8 digits after the decimal point, we need 1,000,000 partial values. Wow. That is a lot. Wow. I didn't think you would need that. How do you prove that? I mean, I guess, yeah. Yeah, how would you prove that? And for each additional digit, we have to add a 0. Ah, wait, but this is 9 zeros. So it ups by 10. 10 to the power of the number of digits plus 1 or something. Even fast computers, and I mean really fast computers, get a bit warmer on the CPU when it comes to really many digits. But the 8 digits are enough for us now, because we want to understand the principle and nothing more, right? As we have already discovered, the Leibniz series is a series with a fixed distance of 2 between the individual partial values. This makes it easy to apply a simple loop to it, because if we start with n equals 1, which is not necessarily useful now, we always have to add 2 in each round. But wait, the partial values are alternately added and subtracted. This could also be achieved with one loop, but not very elegantly. It also makes sense to split this between 2 CPUs. One calculates positive values, another negative values. And so we can simply start 2 threads and add everything up at the end, and we're done. I mean, I guess we could add as many as we want to. Couldn't you divide them by primes, maybe? 1 does every other number, but that's not very efficient, I guess, because you would need more of those. Well, I guess you could do this. You can say, okay, let's say we want to start 8 threads. So it's easier this one. You would have like 8 threads, and then each thread would... So let's say you start at thread 1 takes number 1, thread 2 takes number 2, and so on up to 8. Next time every thread increases their number by 8. Yeah, that's way more easy than the prime suggestion there. Okay, it also makes sense. I was trying too hard to be clever there. This could also be achieved one loop, but not very good. Yes, we have to remember only positive negative values. This is large. Wait, we just have to remember that if only the positive or negative values are calculated, the distances are twice as large. The distance but there's only positive or negative numbers. Only the positive or negative values are calculated. Or the distances are twice as large. Oh, okay, I see. Is it? Isn't it 2? 1, 3. Those are all the positives. Okay, whatever. I must be misunderstanding something here. So that the whole thing has a real learning effect. The first thread call is specified, and you have to make the second. But don't worry, it will work. It will work out. I mean, we just copy this. We increase this. And we set you to minus, and what is this, 5? Is that the total number or something? Count? What is count? No, what is 5? Begin. Why do we begin at 5? Or what does that mean, begin 5? Plus equals 4. Wait, but the formula is... Oh yeah, that's all the... Okay, they're talking about this number here. Now I understand. Okay. I was thinking of the index. Okay. Right. So they start at 5. So 5 is... Okay, so we skip the first one. I guess. So we should start at 3, or oh yeah, we skipped the first one. So this should start at 3, right? Then. Yeah. Okay. If you wish, you can increase the number of loop passes, which improves the number of digits. But be careful. In order for parallel processing to really show its strength, compiler must be given overlays fast flag when it's created. Otherwise, the debug functions slow down the speed to such an extent that seconds become minutes during execution. And you should remove the formatting restriction to print, otherwise you would not be able to see the additional digits. Okay. Well, I'm not gonna do that, but nice. Okay, now we're on to files. Until now, we've only been printing our output to the console, which is good enough for finding alias herping bookkeeping, but many other tasks require interaction with the file system, which file system. I'm just gonna skim through this. Yeah. We know about files. Create a new directory. I mean, I've done a lot of this, so I'm fairly confident that I won't learn too much here. Yes, we get the current work directory. So standard file system, current work directory. You get a thing called a dir or dir, and it's kind of handy to open files in this dir, or create files in this dir, or do other things in the dir. Like first, when I started to learn about file system in Zig, it was a bit like strange because of the different ways to do things, but because you can also say like open file absolute, and you can pass an absolute path. But there's basically almost, well, you can also say open file here and pass an absolute into this one if you want, and that will read it as an absolute path as well. So but I do remember that it's, if I wanted to print the current working directory, that was like very complicated. Then we'll try to make a new directory output to store our output files. Make their output. There's a chance you might run once the path is recreated. Yeah, so I'm going to catch. I mean, you're already saying it. Yeah, we do nothing. Otherwise, we need to return E because it's an error. It could be like permission error or something. Then we'll try to open our freshly created directory. Wait a minute, opening a directory might fail. What should we do here? Well, I guess we can catch this. And there's a whole bunch of different errors. If it's not found, that's weird because we already created it. I guess technically it could have been deleted in between here. But yeah, I think what we'll do here is we just try. So it will just simply crash at this point, and we haven't really done any allocations or anything, so we don't need to clean up anything. Okay, so also you need to close dirs. So we open the dir output and we close it at the end, and we create a file here. We try to open the file, propagate an error up. It is a good habit to close the file after you're done with it so that other programs can read it and prevent data corruption, but here we are not yet done writing to the file. If only there was a keyword in Zig that allowed you to defer code execution to the end of scope. Yes. You are not allowed to move these two lines above the file closing line. Okay, well, wait, that doesn't matter. Well, it matters a little bit because there could be an... does it matter actually? No, it doesn't matter because this function ends here, so it will be closed anyway. Oh, I see. It's too... They're trying to say like, yeah, you should solve the... You have to solve the problem by doing it like this and not moving these lines. Okay. Anyway, to check if you're actually writing to the file, you can either open the file in the text editor, print content, more on creating files. We pass this anonymous struct to the function call. And you can set a bunch of stuff. If you want to append, you don't want to truncate, and so on. Question: what should you do if you want to also read the file after opening it? If I want to read the file. So do I want to truncate it then, because it's empty? So I don't want to truncate, I guess. I don't want to truncate, I want to read. And yeah, that's what I want to do. Go to the documentation here. Can you find a function for opening a file? How about deleting a file? There are those functions. What kind of options could you use? Yeah, I've done a lot of file things, so wait. There we go, past. Now we're on 107. Prerequisite exercise 106 files created. Blah, 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 blah. There wasn't. Okay, hang on. So no. Output. Okay, so it is there. I mean, what do you want me to do? That's what I put to read the file. Okay. Initialize an array of characters, all letter A, and print it. After that, read the content of the file into the array and print the content we just read. Huh? Print out a bunch of A's. Wait. What the hell? Oh, fixed in this. Okay. I was like, this. You can't do this. There we go. Okay. There's any content. Read the file. Alright, so we haven't opened the file. We have a file. Okay, we opened the file. So we need so there's like, you can read directly, okay. Because otherwise you could use like the interface, like the reader interface. But I guess there's like convenience functions here. Read all into this buffer. It doesn't say what type this is. Okay. And we got a read error. or a size. I guess we'll just say try here. And then we print to scream. I know you're excited for zigling time, but tone it down a bit. Can you print only what we read from the file? Successfully read. Change this line only. Oh, I see. There we go. Because otherwise it would print the whole buffer. Because the file could be. I mean, let's just do this. Oops. 44 read all content. Let's make you into. No, you are actually you are a. You ain't. There we go. So we're screaming, and then we're screaming again. Yeah. So we have to cut you off. And there we go. All right. Label switch. Yeah, label switch. This is also like very new. I think it's new in like 0.15 or 14. I don't know. Combining value switches state machines. One such example will be this. Well, true switch. Okay, so this shows like how you would do it maybe in the old. This is kind of how I did it before. And so basically you have an operation and we're switching on that, so either 1, 2 or 3. If it's 1, then we do something and we set the operation to 2 and we loop through again. Now operation is 2, so now we go in here, set this to 3 and so on, and then we're done. But now we have label switches and so we can do this, continue with this label with 2, which actually replaces the value that you're switching on with this value. So now you're switching on 2. So basically we start at 1 here, and then this continues to 2. So we jump over here, we switch again, but now on 2. So now we're on 2, and here we switch again on 3. So we go down here. So that's equivalent, except I guess it's more efficient and arguably more readable. The flow of execution, yes. Which will continue rewrite the value set now 32. Because input not the system input does not have a clear exhaustive pattern. Essentially, we need to handle all cases not explicitly covered with the else. Yeah. All right. So we got a pull request state, drafted and review, approved, rejected, merged. Oh no, your pull request seems to be keep being rejected. How can you fix it? So first we have a draft. Then we are in review, then we are rejected. Okay. Let's change that to be approved. So then approved and then merged, and merged, we're done. Break. Would you know where to break to? Ah, wait, so you're normally not breaking out of a switch. It's kind of fun because like in other languages you usually say break when leaving a switch, but here is like You can't say break in a switch. Are you mad? So you have to, if you're in a labeled switch, you can do this. And now it works. Okay, vectors. Okay, so there's 2 exercises left. Good. So far in ziglings, we've seen how for loops can be used to calculate for utilize. Ah, okay. Vector. Oh, okay, yeah, vectors. So I have a lot of experience with vectors as well. Most modern CPUs can execute several execution calculations are performed within registers at the same time. Yes, there's registers that can hold a lot of data, and then there's special instructions to also if you have a large array or several large arrays even to perform calculations on those arrays very, very fast. These are known as single instruction multiple data instructions. SIMD instructions can make code significantly more performant, and I'm using it in my physics engine for updating positions and velocity and applying gravity and stuff, and it makes it super fast. To see why, imagine we have a program in which we take the square root of 4 floats okay, square root, notes that the half array should contain blank data which nothing happens. What a waste. When able to use spaces, that is the core of this is the idea at the core of SIMD. Okay, sure. Most modern CPUs contain specialized registers with at least 128 bits for performing SIMD instructions on a machine with 128 SIMD registers. A smart computer would probably not issue for square root instructions as above, but instead pack the floats into a single register and then execute a single packed square root instruction to do all square root calculations at once. For example, yeah. So it goes pretty fast. Vectors. It's a built-in type that it's kind of like an array, but you can do a nice thing. You can do these. Plus, I'm using this in my game code, and it's a really nice way of working with positions and stuff like that. Defining vectors is straightforward, no library. And it doesn't have to be only 3. You can have any amount of elements in these. Intuitions that apply the base usually extend to vectors. Yeah, so it's also very nice. You can do casting, float from int, conversions on the entire vector at one time. You don't need to do it like separately on each element. And here you take a scalar value and make it into a vector to be able to, yeah, you can use it to like multiply by scalars or do things like that. And here is like, okay, so what they're doing here is, okay, V8 is set to this, and then we're adding, we're doing a fold here. So we're taking each thing and we're adding them together to get the result. Okay, I didn't actually know that there was like add and these. I think I might have known. I mean, I know about reduce, and I've used it for like comparisons. You could do like and or. Fixings automatically assigned to vectors and vice versa. Yeah, pretty cool. Now let's use vectors to simplify and optimize some code. Eva is writing a program in which they frequently want to compare two lists of 4 F32s. It expects the list to be similar and wants to determine the largest pairwise difference between lists. Wrote the following function to figure it out. Calculate max pairwise difference. Old. Yeah, so this would be like the non-vector way of doing it, looping through each element separately and doing some operations here. But now we've got vectors. So the abs diff vec. So I guess, are we doing, so A, B, we're doing A minus B, okay. I mean, I guess it doesn't matter actually, since we're taking abs here. And then we reduce this, what do you want to be? Was it min or max? Max. Yeah, so very, very more nice. Yeah. Okay. Quite a simplification. We could even write the function in one line. It would still be readable. Since the entire function is now expressed in terms of vector operations, the C compiler will easily be able to compile it down to machine code, which utilizes all the powerful SIMD instructions and does a lot of the computation in parallel. Very, very cool. All right. Okay, so now the last one, quiz 9. I think it's the last one. We got 999 as well. Okay. Quiz time. Toggling, setting, and clearing bits. Another exciting thing about Zig is simply embedded for suitability for embedded programming. Your Z code doesn't have to remain on a tab up. You can also deploy code to microcontrollers. This means you can write Zig to drive your next robot or greenhouse climate control system. Ready to enter the exciting world of embedded program? Let's get started. Some background. Common activity in microcontrollers, setting, clearing bits, input and output pins. This lets you control things, blah 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 blah. This microcode included. Below is a pinout program famous at Mega 328 AVR microcontroller used in the primary microchip popular microcontroller platforms like the Arduino Uno. Yes, pinout diagram for this thing. I think I actually have one of these in a box somewhere. Yeah, so we got a bunch of pins and they have like different things. Here's ground, so, and here's the input voltage, and I think, let's see if I remember here. Got a bunch of things here. So some of these are, I think some of them are like can be, what's it called? Analog. Is that what it's called? Like analog and yeah, I don't know, whatever. Drawing inspiration for this primary, we'll use pins for port B as our mental model for this quiz and a bit maturation. It should be noted that the following problems will simulate modifying bits as real hardware registers, but in actual microcontroller code, port B would be defined something like this. Volatile U8. This lets compiler know not to make any optimizations to port B so that I/O pins are properly mapped to our code. Because it's of the pointer thing. So if you wouldn't have this here, it might mess with the pointer maybe. I don't know. To keep things simple, the following problems are given using type U4. So applying the output to port B would only affect the lower 4 pins. Of course, there's nothing to prevent you from swapping U8 with U4 with U8. You can control all of them. Okay, so we got port B. See if you can solve the following problems. The last 2 problems throw you a bit of a curveball. Try solving them on your own. If you need help, scroll to the bottom of the main to see in-depth explanation of toggling, setting, and clearing bits in Zig. Toggle pins with XOR port on port B. Initial state, bit mask, what's going on here? Well, we're doing an XOR assignment. So this XOR'd with this. I'm pretty sure what's going on. This one should be a 2. And this is a 1. So it's a 3. This is 3, right? Okay. What? I don't. I mean, I don't understand what I'm supposed to do. If you know, toggle pins. Okay, we're doing a whole bunch of. Okay, wait. What's going on? I mean, okay. What's missing here? Okay, here we go. What's missing? Okay, I guess this is to show some sort of formula here. This is bits 1 and 0. I see, this is the bit mask. Okay. So we start at 1, 1, and we have a bit mask over there, so everything is set because we're XORing against this with this, okay? Here we have this, and we are setting it a reset port B. And we have a bit mask of this. And we need to make it into this. I mean, we could choose to either... I mean, we could do this, I guess. To take this operation... Yeah, you could also use an OR to get the same thing. But I guess that's not what they want. Reset. Oh, I see. So they reset, so they mean that they set it here to something else. Okay. It's not... I thought it was like the operation of this whole thing. Like, what the hell are we doing here? Okay, so 1001. The result should be this. I mean, it's the same thing again. Clear pins with and not. Okay, so now we're on and not. Okay, so we got 1110, and we should have 1011. No, wait, we should have this 1010. And a not. What character is missing here? This is so we should do a not here, because this only sets this one, and this is invert, so we're inverting that to get this, and then we're ANDing only these. Get through there, yes. And here we're missing what? 0111, 0110. So if we AND these two, isn't this already correct? What am I missing? This should be 1. No, wait, this is 0. Sorry. Wait, this is... No, wait, this is 0 shifted to 1 becomes nothing. No, it's 1 shifted to by 0. That's the... Okay. I was thinking it other way around. So this should be 1, which is 1 0 0 0 1, and then we invert it so it becomes 1 1 1 0, and then we AND it with this. So this is 0, this is 1, so that should be 0. This is 1, this is 1, so this should be 1. This is 1, this is 1, so this should be 1. This is 1, this is 0, so this should be 0. What's missing here? Bitwise not operational type comp time int. Oh, I need to cast. Okay, or I need. Okay. This doesn't count. Okay. There's something incorrect here. Expected output is... Wait. 1. No, this should be 2. Yeah. 1 0 1 2. Okay. Oh, this should be or. Man, I didn't see those things. I wasn't looking there. Okay, there we go. Yay! Checking the end. This is the end for now. Hope you had fun. Yeah, it was pretty nice. I mean, yeah. Okay. Pretty cool to go through everything here, and I did learn these things here. So I learned a couple of new things from going through everything here. From using Zig for like a year or something, and not really, well, I never went through ziglings, and well, I read a lot of documentation, but not, I never like went through everything, just things that caught my interest and tried to solve specific issues or specific things. But these are the things that I learned here. I guess you could add like things with the thread, but I have used thread before. Well, anyway, this one was interesting. This is probably one of the things that I would use. Maybe, we'll see. From the things here. Comp time, no. And this one, this is a huge, like knowing that where does this value come from? Like the compiler puts a bogus value, which is in hex, like A, depending on, it just fills the space with A if you forgot to assign an undefined value. So that is really nice, because if you get a seg fault at OX A, you know that you messed up some pointer somewhere and forgot to set it. So that's really cool. All right. Cool. All right. Well, that is it for the ziglings. Nice. Now I actually started playing around with making a parser in another project here, which is I just love these things, like making program languages or making something. Yeah, I don't know. Sometimes I just wanna make a parser and be able to read some code and do something with that. And I made this sort of infrastructure for reading a string with a reader and running a parser that can report errors, and you can pass in like, it's kind of like a monad. So this is kind of like a Zig version of a monad here. We're running the parser, we're passing in this parse char, which produces, you could say, a monadic value in this monad. So this produces a parser function, which is well, actually not a function, it's a struct, but it's kind of cool how it works actually. So this is like you're defining the parser to be parsing a character Z for Zig, and then we run this parser and we can see if there was an error, we can print this out. Otherwise we can show which character we read here. And here's the input. So the input is a reader, a fixed buffer reader that just has a Z in it. And if we run this, well, you can see here that we get this read char Z. So you can also get like a value out of it if you. We can make a like a arithmetic later. But if you change this to a C, now this produces an error now. And so we get this expected char Z found C. So it's kind of cool how this works. So if we look at these functions here, the run parser takes a parser context, which you initialize outside and pass in here, and then it will, if there are like errors and stuff, it could populate it with errors. And so if you return an error here, we will sort of store the errors and return an error, so you can catch it, and you know, you don't only have this run error string, you actually get like the errors that you can look at and stuff. But anyway, so then you also pass in a parser. Now this has to be an any type. I mean, it doesn't have to be. You could put in a comp time. You could do it like this as well, but I feel like that's just clunky. Much easier to just pass in the thing as an any type, and then we like validate that it's actually a parser function that you put in by calling this function here, get parser element type of parser. So this is a comp time like type function that takes this type and it checks that it's actually a parser function. So first we check if we have a declaration called element on this type, which all the parser function has. So that's a convenient way to get the like the element type, which is so yeah, okay. So the element type is like well, it's easy to see if you look at this. Parse char is a parser function that kind of has a result of a char. It's whatever char you are reading, it produces as a value here. And then you can extract this value if things went well. You can extract this value. Okay, now you don't really see the type here, but this is a U8. That is the result of running this parser, which is the type in here that you get out. And well, here's so well, let's see, where's the run parser? Yeah, so basically we're calling this run function on the parser, which if you look up here, is just a function that has, so the parser function is actually a struct, so it's kind of weird, but it's because we need some extra data. Sometimes we need some extra data that we pass into the parser. It's kind of, I'm calling it a closure here because that's kind of how I'm using it. So we got a closure that is a pointer to an opaque, and we pass that into the parser when calling it. So here we're calling run, which will call the parser with the context and produce the result. And here we're calling parser with the context and the closure and produce the result. So it's just a convenience function for running the parser. We're executing the parser here, and we get the parser result out. Now this could be either an error or a success. If it's a success, we get the value out. If it's an error, yeah, we have an error. Yeah, so and then you have parse char. So this one, now this is kind of like a function that produces a monadic value, you could say here. So this is just a very simple parser, and it takes a configuration here, which is the character that you're supposed to be able to, you're supposed to read. And so in our case it was a Z, so that means that we expect a Z next, basically. And we get a parser function out. And what is that? Well, we construct it here. So the closure, that is the configuration that we pass out here. So in this case, I'm kind of using the pointer space as a storage for this character. So I'm using pointer from int to kind of store this, a kind of weird way of storing this thing, but it works because this is a U8 and this is a pointer, so a pointer is like 32 or 64 bits. So this should always be like fit in here. And then here's the parser function. So we're defining the function here, but we need the closure because you don't have access to this. So we have to like have a closure that we pass in. And that is what we call that. That's why we need a struct here to define this closure, so we can call it later. And this one is just this is the actual monadic function here, or the monadic value, you could say, that takes a constant and the closure and the result, or returns the result. And here we get the closure character back from this pointer. And then we have and then we use this reader to look at the next byte to see if we get a byte out. It could be an error here, or it could be end of stream. So we have to take care of that. And then we check, okay, is the byte equal to this char that we want? Or if it's not equal, then we have an error. Otherwise, we consume the byte now because we know that we should move forward, and it's a success. And then we we return this byte in the result. So that's a very the kind of almost one of the simplest, I guess, parsers. I would like to write a parser for a number now. So if we kind of copy this and we say parse number, and we don't really need a configuration for that. I guess we could say what type of number it is, maybe. I guess we have to ensure that it's a number. Is there a standard function for that actually? Is number? No. Types. hang on a second. I'm gonna look in zig. Is number, no, is integer, LLVM builder type. Okay, now okay, I guess we can make a number thing here, is number. So, or I'm gonna do this, ensure number from time t type, and this returns type, and we can simply, you know, we can simply have a series of if else, I guess. If t is not equal, if t is equal to u8, return t. Wait, this is stupid. No, we have to do like actually, you know what? I'm not gonna do that. I'm gonna just use the type, and then if at some point it has to be converted into this type. So that's where the issue, that's where the problem will arise here. Now we don't really need a closure, so I'm just gonna say undefined for that. Okay, so we have the parser, and the result should be a t. Okay, and we don't need this. Okay, so we're gonna try to read, I guess we'll read digits. So this is where if you define primitives of the parser primitives, this is where the monadic style gets its strength. Now we don't have the primitives to solve this easily, but if I had, for example, like parse digit and parse char of like a dot, if you want to have like floating point numbers, let's not do that for now, but let's just, okay, I'm just gonna start with just reading one size numbers, like it should, the digit is just only one digit, it reads one digit. So actually let's actually call this parse digit instead, maybe, and then we always receive like a U8 or something. So this would basically be the same as parse char here. We're picking the byte, expected digit, found end, and then here we need to check if it's a digit. So if yeah, I think ASCII, yeah, this, I learned this from ziglings. We have ASCII and we can say is digit byte. If it's not a digit, then we return an error, and this simply checks between 0 to 9. Yes, we return expected digit, found that. Okay, then we take this byte and we report a success, except now we want to convert this to an actual digit, so we have to do this. Okay, so now we have our parse digit function. Let's change this to U8. You are unused, so I will do that. Okay, let's go back to main. Okay, so now instead of doing parse char, we're doing parse digit. We'll import this. And have to pass in anything. And now this is the digit instead. So red digit. Okay, but this is now gonna be an error, right? So if we run this, it says expected digit found C. And so if we now say 9, we read, oh, I see. Now this is actually a number now, so we don't format it with ASCII. There we go. So now we read in 9 here. All right, cool. Okay, now what I want to do is well, I kind of want to make the primitives and then be able to combine them, because that's kind of the power of the monad here. So parse digit, I mean, parse digit is kind of the same as if you would have a function called parse. There's usually you have like one of, which means that you have a list of things, you have a list of parsers that you want to try. And if so you want to find the first one, and you have to like go sequentially to test each one. The first one that succeeds, you're gonna use. Is how I'm thinking about this function here. So we'll do a parser function, and the thing is, this is gonna be interesting because this will probably be like an anytype parsers. It's gonna be like a tuple of parsers, I'm pretty sure, and then we have to get parser element of the type of parsers. However, parsers is a tuple now, so I think I'll make a separate function for this, get parsers elements, if you have multiple parsers. But that won't really work. This can't be type safe. It's like it's always gonna be like some sort of union. I was thinking, like, should we like spawn a union type out of this then? I mean, we can try. I think the actual the actual thing here is probably not that I think the parser, so let's do well, I think here is where we need an actual allocator as well. Some of these you need to pass an allocator actually. And this will be allocator create. Let's have the closure will be allocator create. So we need to create the space for this parsers. And then this would be the closure, but we also populate it with parsers. But that's just, it's gonna be a tuple. It's gonna be like a bunch of pointers, basically a bunch of pointer functions. No, actually it's gonna be a bunch of structs. Well, okay, it doesn't matter what it is. We create space for it, we populate it. It's not com times what I'm trying to get at. And then we set this closure here. Now let's say we have this thing. We do need closure. the closure here. And this one, let's just say t is equal to that. So return that. Okay. Now the parser function is going to be actually this might be more high level than I thought, like, because okay, let's actually wait with this one. Actually what I want to do is make a sequence function. Now what this is gonna do is it's gonna parse things in a sequence, and you probably want to discard the values as well. We'll start there anyway. So we'll start with parsers. This is gonna be a list of any. Can you have a list of any type? No, it has to be a tuple because the parser functions can be different. Yeah. And then this returns a parser function of basically we need to get the last element of this tuple. So this will be like get last parser element type of parsers. Now this is way easier because we don't have to like merge the types. So this would be, unless we say that one of is always gonna be the same type. Well, we'll see. Get last parser element. So this will be we get the type and return a type. So the type is going to be the tuple type. So we'll grab the fields. So this will be, we always know this to be a struct, and we're looking at the fields, and then actually we don't need to do a loop. We just need to grab the last one. Parser element. So we can call get parser element, which we do already have on fields of length -1 dot type. All right. So that gets the last tuple, the last parser element there. Or we could just do void. That works as well, I guess. Whatever. Let's just do this. Okay. So now we have to return a parser function. So we have closure is gonna be. This is gonna have to be. We're gonna have to allocate this actually. And then let's also do this. Get last type of parsers. And closure, yeah. No. We need this. Oops. And then you are a bunch of stuff. Okay, now closure partners, closure parser. So this is gonna be the parsers, which is gonna be the same type as the parsers, and we just do a pointer cast. Yes, very good. Okay, so now we have access to those. Then we wanna like we wanna run these in sequence. Actually, you know what? We should probably have access to them. Maybe. No, we don't have access to the actual values. That's right. Okay. I was thinking more of the type, but so this would be like type of this, and then type info dot struct dot fields. Oh, hello Mortu. Currently, coincidentally, also learning Zig and ziglings. Currently at 66. Oh, nice. Yeah, I just finished. I've been doing it for 2 streams. This is second stream, and I finished it like, I don't know, half an hour ago or something. Cool. How are you liking it so far? Let's see. Inline for. Okay, so we're going through each one. We should run. So let's get the parser by doing at field closure parsers. Oops. Field.name. So now we got the parser, and now we can say run context, and we need to grab the result. Zig is strange in some ways. How when a for loop item is a variable name. Yeah. The capture, it's a bit of a strange syntax, but you do get used to it. I do like it. It has a nice like there are some nice uses for it. But then this one exception, you can actually use star to make a pointer. Yes, I mean, I would say that was more like a modification to the capture, that you're modifying the capture not to be just a copy, but you're saying now it should be a pointer to the original. So you can have it, or you can. Yeah, it depends on what you need. But yeah, it's a little bit getting used to it because it's so unique. But I've been using Zig for about a year, and I really like it. I feel it's very like new and fresh to me. Wait, how is this unused? I'm using it down here. Oh, that. Okay, so we call this whatever, like this. Okay, so the idea is that we have a sequence of parsers. We're gonna run through each one, take the result, check if there's an error, If it's an error, we bail out with this error. If it's not an error, we continue. And then in the last one, we will return the result from the last one, basically. Not sure how useful it will be to just return the last one, but you can't make any other changes to a capture. I expected the same as other places where you use address to get a pointer of it. Yeah, that's kind of the other way around. It's that is true. I do agree with that. It's kind of weird how you put star there, but you do get used to it. But it kind of, yeah. It doesn't make sense in that way. Like if you see it that way, it doesn't really make sense. Which I kind of agree there. It's kind of backward. Let's see. Yeah, okay, so we check, so we switch on result and we check, okay, is it an error? Then we return the result, which is an error. If it's a success, we will basically just cast away this and do nothing. Basically now we're gonna loop through, we're gonna loop to the next one and do the next one. Okay, I think, yeah, and then the last one, I guess we have to make a if here. If we're gonna use the last one, let's just not use the last one, whatever. Let's just have void here. And then in the end, we will return report success with a void value. All right, cool. So I think we've made a sequence parser, or yeah, this is like takes, you know, a list, you could say a list of monadic values and merge them into a sequences. This is one of the strengths of this. I like Zig, I just think that it's not entirely consistent everywhere. Yeah, that's true. I mean, it's still in heavy development. I would say it's like, it's a kind of far away to be, you know, it's still, you still get like major breaking changes when you upgrade like the major version. Alright, so we have this sequence. Now we can do stuff like we can do things, yeah, I mean, we can do things like this. So let's see. Now we don't get the value out, but we could say zig, and let's import sequence here. And zig will be, you can parse this now with sequence, pass in the allocator, and here's the parsers. So we'll parse char z, I, and then G for zig, and then read success. Oops. No. Unable to resolve comp time value. Hang on. Comp time value. Well, allocator is not supposed to be comp time. What comp time? Comp time only return type parser functions evaluated at compile time. What? Why is it complaining about allocator? Call to function with comp time only return type. So is it saying that the parser function with void is a comp time only return type? This? Now I'm confused. It's been 10 years in development, yeah. But it's a lot of people are working on it. It's there's a lot of things happening, and yeah, I mean you can see the progress on their GitHub project or the repo. Yeah, I think they're moving to a good place, but we'll see. We'll see what happens. Let's see. So what programming languages have you worked with before? I don't really understand. It's saying this return type needs to be comp time for some reason. Comp time only return type parser function void. I mean, what if we just changed it? Wait, struct requires comp time because of this field. Parser constant and take parser result T. Use of this for a pointer type. Oh, use. Oh, okay. So you, instead of doing this, you say this to get a pointer type. And expected pointer type found struct. Oh yeah, so okay, so this is not this needs to be a pointer. There we go. No wait, this needs to be dereference. Type of parsers. Okay, let's just do as type of parsers bycast closure dereference like that. Okay, align. All right. expected is found U8. Ah, okay, yeah. So this is another one. Now we want to have a map function. Worked a year with C# and after that I worked with Java, Kotlin, never really touched much else. I wanted to learn a new language. Okay, nice. Did you make that and set up yourself? Yeah, most well, I did. I set up MVim, like the config and everything from scratch. I'm using Lazy to load a bunch of plugins, but I didn't, I didn't start from like one of those. I wanted to, have total control of everything that I'm doing. So I didn't start from one of those like pre-packaged configurations. Not that there's anything wrong with that, but that's just what I wanted to do. I always wanted to go through, like, start with NeoVim, and the start would be to just configure it to be how I want it to be, basically. And I took the time to do that, and I ended up with this. But it's like also like sometimes I add things over time and stuff. No, I started from scratch. Okay, yeah. And yeah, I made a bunch of custom things. Let's see. Parser. Yeah, okay. So we did a map. Yes, that's right. So map, and then yes, fully from scratch. No, no, starter config or anything like that. Just install the NeoVim and start to write the config from zero configuration, basically. So this one, we need a map function. So mapper function. And this one, I think if we just put any type, we could infer the from and to. So it should be a function that takes one argument and returns another argument, or returns a result. And then this would be the return type of that. So we do type info type of mapper function, and it's a function. I don't bother to do like proper things here. So this is the return type. Actually, if it's null, that means it's a void, so we can do or else void. So that's what it should produce. And we also now want a parser function that we should map from. And this one is but this is also any type. And then we have to make sure that so let's do get parser element of type of parser. This is let's say A, and then B is gonna be whatever's the return type here. So A is the input, B is the output. And so we will say if type info type of mapper function dot params 0 dot type is equal to a. Well, if it's not equal to a, then it's a compiler error saying type mismatch of mapper function. You can also like expected type name a, actual type name. I'm calling it P for parameter. P is not equal to A. Actual will be P. I guess if it's null, that might mean it's a void. I don't know really, actually. I'm gonna do this. Learn how someone set it up and was working, but everywhere I read it takes a lot to maintain, so I'm just rolling with Astro and with my own modifications. I mean, there's really nothing to maintain. I don't really know. I don't have to go as, it's not like it's breaking down. It is what it is. I mean, it's kind of like if you want to, like, let's say you want something new or some, you know, you want to start with a new language. Sure, I can get that. Like, you want to start with a new language or a new tool or something, and there's no like support easily for that. But I think it's pretty simple. I mean, it's way easier now, I think, than it was with like Vim. Because Vim was so clunky sometimes with its scripting language, and okay, I'm not gonna hate on that, but but like the async stuff and the tools that was available there felt, at least when I used it, but this was years ago, but it feels like night and day to use NeoVim actually. Okay, so if they are not equal, there's a mismatch, and that's fine. All right, but then we have the resulting type, so we should produce that. And the closure needs to have both of these. So we need to create kind of like a struct here that has the mapper function is the type of mapper function, or it could be like a pointer, like a constant pointer to that. Actually, they should, no, parser is the only thing that is an actual thing that we need to have. Yeah. So I'm just gonna say this should be type of parser. This is the actual thing we need to save. The mapper function is just a function, so that's just a pointer. But we need the pointer though. But we should have the pointer here, maybe. Do we have, this is the interesting thing, like in comp time context, do you have context in this function here? I mean, we do have b. I guess we'll find out. So let's create this parser thing, and we will populate that. And then here, this would be closure parser as pointer to parser. let's just do a pointer cast. Fine. And then this would be like a. Oh, this is actually just type of closure. Okay, and then we don't do this. What we do is we take, well, we grab the result. So this is like the functor map function. What am I working on? I'm working on a parser, like a monadic parser in Zig for some reason. I just had this idea and it kind of grew here. Well, I barely getting started because I barely have I'm currently defining so basically we have this monad, which is a parser function that can contain a value, you could say. And I'm writing a map function that maps this that maps a monadic value to another with this map function. It's gonna be interesting to see how this will work out. Okay, so we have this parser here. Let's see. We run this parser now. So closure parser dot run, and we need the context. So we grab the result. We switch on that. So this could be an error, and if it's an error, I think we just return this error here. Result. If it's a success, we will return report success. However, first we apply the map function. So mapper function to, and we get the value here, this value. All right. And allocator. Right, so we actually need to pass an allocator here as well. Yeah, it's a bit annoying to have to pass the allocator, but I guess it's necessary, unless you allocate this before, but then you just move the problem a little bit. Oh yeah, so this is the sequence, right? So this one, it's saying this is a U8. Oh yeah. So now that we have the map function, we can go here, we can import that. And you can make this more convenient as well, but here I'll just make a function called make void or something, or map to void, and this would take a parser and return no, this takes any value and returns a void. All right, and then we will map. I have to pass allocator, map to void there. Okay, so it doesn't look clean, but we can fix that later here. Let's see. Type mismatch. Wait. Okay, A should be U8. and P should be the first argument. Oh, I guess maybe since it's an any type. Okay, maybe this is like, it means it's any type actually. Okay, then I'll just do this. No? Well, here we have to like, maybe like cast the result, because it doesn't make sense. Like the error result should also be a void in this case. So we should just cast this somehow. Maybe you can't actually. I mean, this is a U8. It should hold a U8. Like they have different size. But this should have like no size. Or no, it's a pointer. It has a function pointer. It has 2 pointers. No, wait, it's the results. Sorry, the result. Oh yeah, so this is a union enum. And yeah, this is the type. I mean, I guess maybe we could do report error. We could wrap it. And wait. No, actually, let's. Maybe we could do this. We just copy it, make it like a nice package there for the return type to be correct. Okay, I think all the compilers was fixed. So basically, yeah, because this sequence here, no, what happens if we just remove this now? Will this be an error? Yes. Because this is also okay, so we'll do the same thing here actually. So we didn't need a map, but it's good to have because yeah, it's one of the main things that we're gonna have. Okay. So now let's see if this works. Yay, it works. And if we, for example, do this, there's an error. Expected Z found C. And if we change U to C, it expected I found C. Now, so this works, cool. Now, you may notice here that it still says 1, 1 because I haven't implemented, you know, line 1, column 1. I haven't implemented this to actually increase these things. But yeah, it's kind of like a proof of concept. It does work. It's a bit clunky to define these things, but you know, the more helper things like this you could define, the easier it will become. So next part would be to define a function that says parse string, where you can basically just say sequence and then each character like this. So let's try and do that. Parse char. So let's do parse string, let me just copy this. Now this will return a string, and we can put a string in here to match with. Now the string is comp time known, so maybe it will be available in the closure. I'm not sure if you have to do this here. But okay, so basically, actually we don't really need the sequence for this. We can just do an inline 4 here. Inline 4s, we get the character, and then we... No, wait, we can't do an inline 4 because we're not in the monad thing. No, we have to do a sequence, yeah. So we return a sequence. Oh, we need an allocator for this. And the parsers. Now this is going to be interesting. The parsers are going to be a tuple that's... Can you actually make this tuple here? Is the question. I think you can make a struct with variable... Yeah, you can make a struct with variable fields. You should be able to make a tuple with variable fields. So let's do like comp time. I want to make the tuple types, the tuple type, and we are going to have the fields, which is built-in type fields, struct fields. And it's a slice. Let's make this. So we set it to an empty slice, and then we return type of a struct, and we say tuple is true, fields is fields, declarations is always an empty slice. And I guess we'll put auto there. I never know what this is, what that is. Alright, no, not return. This will be break like this. Oops. And okay, so now we need to build up these fields, and we're gonna loop through S to get that, and then we're gonna say that you are equal to fields plus built-in type struct field, and actually I think you need to be that, and you need to be const, and you have type is, what's the type? The type should be a U8. Okay, let's just do this for now. This is gonna, I think this is a bug in the LSP. It wants the fields to be here, but this is actually the list. Okay, name. Ah, wait. The name. But this is a tuple. Tuple types. Oh, you can just do this maybe. Tuple. Create unique tuple. Tuple field name. Oh, this is how you do it. Okay, that's weird. Numbuff. Huh. Okay. Well, we can just use this, and then we'll have like we just put a we'll just do like field types, which is a list of types, and then we'll loop through here and we'll say you are field types, and this is a type, and then you will be U8. Actually, you know what? We could just do this actually. This is a list of types. We will do type U8 times s dot length. Okay. And we don't need to construct you. We can just actually now we can just do this directly here. There we go. Okay, that was a lot easier than I mean, presumably, assuming it works, is what I was trying to say. All right, parsers. Okay, so now we want to create a value of this tuple. We have the type now that we want to pass in here, but we want to create this thing. So I think what you could do is you could say, first you say like, first we have this tuple. This is a tuple, but we put it to undefined. So now we have a place to have it, and then we just do inline for s, we get c, and then we say tuple wait, how do we access? No, wait, because we can get I, and then we do tuple fields of tuple, and we can say fields of tuple with tuple fields I dot name is equal to C. Okay, and then we pass that in. We pass the tuple in there. There we go. And hopefully that works. Now let's parse this string. So instead of doing this, we try parse string zig. And there's some kind of error somewhere. Ah, the string was ignored. Okay, well, let's read the string. And we can print it out there as well. Cannot assign to a constant. Ah, this needs to be immutable. There we go. Okay, what's going on here? Oh yeah. So we need to sort of map this now. So let's map it. And we can pass the allocator. And we need a mapping function. So I'm just gonna define this function here. And this is gonna be taking I guess it takes a void and returns a string, and then we return s because that's should be comp time known, so hopefully that works. Oops, unused. Oh, yeah, okay, yeah. This needs to be parse char. That's right. There we go. Expected U8 found. Yeah, so this is parser. Actually, this is parser function U8. There we go. Okay. I mean, it does require a little bit of when you're defining these things, even if we have sequence, we have map, you know, just passing in a tuple to sequence requires some work. So it's not the easiest thing to work with, but it is kind of like a proof of concept here. Anyway, so now we have the parse string. Let's see what this says. Yes, so now it says that found expected I found C, so this is the same thing. Let's pass in zig, and yay, it works. And if we test the last thing, expected G found A, so that works. Cool. All right. Okay. Well, that is kind of like a. This is sort of like you're reading a static thing. We don't have a way of like take until or something like that. Parse digit. I mean, really, these both should. I should really take these two and make this into one, which is like take one or something. And this would produce a byte. We don't have any configuration or anything. This is undefined. We don't need to grab you. We get this expected. Okay, so this is kind of bad now, actually. We need like an error message actually here. Expected message maybe. Let's make this like comp time. Expected. But here we don't do this. What we do is we consume the byte and we report the success. Okay, so now when we have this basic block, there, when we have when we have this basic block, we can instead do this one. Okay, this one requires a little bit of other one, but this one could be just, no, this also requires a little bit. Okay, we need a filter as well, or something like that. Filter, or is it filter or what is it? By the way, there's a compiler.env that gives an easy way to compile stuff with Zig as well. I can run F6 compile option and shift F6 for rerunning the previous option. Oh, cool. I mean, I usually run, I use Overseer, which is a nice task runner. And then I just map, whatever command I need in order to run. So, but now for this one I haven't done that, but I usually do like you know, F5 or some. I usually use like F5 and then where is it, Overseer run command, and then it's like sig build run, no, not run, yes, run, something like this. No. There we go. No remap. Okay, and then it will run. I can press F5 so it will run like these ones. Compiler.env depends on Overseer. Oh, okay, I see. Well, I kind of skipped the compiler. Yeah, I use the Overseer directly, I guess. All right. Well, that's good to know. Thanks. I never. Yeah, I usually don't like. I went through most of like. I went through like popular things one time, and then I just picked the things that I thought that this would be nice to have. But I am leaning towards to having a lean, you know, setup, and not too much stuff in there, basically. Okay. What did I think about? Oh yeah, so in order for these to use this, we need to have some sort, because both of them are kind of applying some sort of, like we're taking one byte, but then we're applying some sort of filter or some sort of condition on the result. So filter is kind of weird way to put it. I guess condition maybe is better. Let's do that. Let's say like condition, and we want a predicate function, and a parser, and kind of like it's sort of the same as the map function. So let's actually take all this. Where's the condition? Except this is a predicate function which should return a bool, and this is still gonna be, this is just gonna be the same type as the parser, and we will get the T. We will, I'm just gonna check if this is a bool. Well, this is gonna be a compile error anyway. We don't need to no, Larry, just check that they are the same. That's fine. Type mismatch of predicate function, expected T, actual P. There we go. Mapper function, no, predicate function. So we get this predicate function. This should return a bool, And we need to store the parser. So that's good. We store it there, we get it out, we run it, we get a result. Now, if it's an error, it's an error. If it's a success, let's remove this. If it's a success, we will say, well, actually, we want to now check. So we want to check if predicate function. So now we want to run this on the value, and if it's true, we return a success. Otherwise, we need to return an error. But which error should we return? Is the question. So I guess we could maybe then have a format. So it's kind of like expected this. Yeah, that should work. URT. Okay, let's just put this here. Message. Wait. No, expected message. Alright. Okay, now we can say. Now we've basically broken out these into these two functions. And so, for example, the char, which should be the most easiest one. I don't think we actually need the closure here, to be honest. But what we'll do is I will. Whoops. What? Okay, there we go. I'll comment this out, and instead I will try to use now built-in functions here. So we will return. So first we have take 1, and expected is well, this is just okay. I'm gonna say, okay, I could just do this actually. That's the expected message. Actually, we could say char. Like this. Since it's comp time known, we can do this. Okay, but this is not enough. We need to also now do a filter, so we need to add a condition. Oh, now we actually need an allocator here. Okay, sure. We're probably gonna end up needing allocator for every one of these anyway. Which is probably why we should put these in a struct instead that already has an allocator, so you don't need to do that. So you only pass around the parser struct. Maybe. Okay, well, we can figure it out here. So we'll do condition and the predicate function. And then the parser, and then we have expected message. it should be the same, so I'm just gonna say that this is whatever's in here. And you are expected message. Okay, we got some. Okay, now we need the condition function, which would be something here. So let's add a condition. Let's predicate. And you return a bool. You will take a U8, and we'll just return C is equal to char. So that is our predicate. And of course, now you need an allocator. Root parser function U8 ignores. Oh yeah, so now we need to return this. There we go. Yeah, so this replaces that entire thing, which is pretty cool. All right. Nice. Now, now we can do the same for digits. So let's say we expected a digit, but that's the only thing we did have. And this, we get a char here, and we have, where is that? Oh yeah, standard ASCII. So we'll just return if this is a digit or not. Okay, and that's replacing all of that. Very nice. Okay, well, we don't know if it works, I guess, yet. You need an allocator. That's also the downside, but yeah. Anyway. Okay, so now, well, let's run this again. I guess now we can use this to see, and we get a success, and we can change this, and we get an error. Yeah, so it works. Cool. Now let's try parse digit, I guess, again, to see that it works. You need an allocator. We're gonna say you are 5 here. You are, I'm just gonna ignore this. Wait. Oh, now we're not. Okay, so since there was no error, it worked. And now there's an error. Actual 122. Okay, so the actual needs to be printed as, oh, it's Annie, so not good. But I think we're always going to basically handle the strings, so it's either gonna be like a U8, or I wonder if C works for arrays. I mean, we could do this. We could log info, and then C, and then we'll have hello. No, okay, that didn't work. Okay. Well, whatever. We'll fix that when it comes to that. Okay, cool. So that works. Now this needs to be string. Yeah. There we go. Cool. Are we ready to make parse number now? I don't think so, because we need to have like a loop of some kind, which we don't have. So sequence is just for a known number of parsers. So what we need is like something like take until or something, like take while, and then you can pass in a parser, perhaps. Okay, let's do this. Take while. So I'm gonna say this. So take while, we pass a parser. Now this parser is gonna be passed, or it's gonna try this parser again and again until it fails, and then the result will be a list of values that we managed to parse with this parser. So this will be a list of get parser element type of parser. And what would the context be here? Well, we need a parser, and yeah, I think that's what we need, the parser. Closure parser is equal to, well, this is just gonna be like type of closure is equal to closure point cast. We don't need to loop through these. Okay, so what do we want to do here? We want to create yeah, let's just make the values list here. Let's make this an array list of t's. And we will say, so I guess we'll have a while true. We will run the parser, closure parser, run with the context, get the result, and we will switch on that, and if it's an error we will just return the error. Except now we need to wrap this to get the new type. If it's success, we are going to No, wait, we don't return the error. We don't return the error. That's right. What do? We report a success with values we have to return this, and then success we will just continue. Well, what we do is we get the value out and put it here, append value. Allocator as well. I think we have the allocator. We have the allocator on context, so we can use that. So we append that to the values, and then we continue the while loop, which we don't really need to specify because we're at the end anyway, but whatever. Yeah, so if there was an error, that means now we've done. We should also, okay, this is where we should use try parse as well. Yeah, we have to use try parse here, or we should, yeah, we have to sort of so we don't really have this functionality yet. What we need to do is roll back, because now the context may be weirdly out of sync here. If we advance, like we're calling this parser function, that might advance the reader, or you know, the context like line and column and stuff. But if we have an error, we should roll that back. So you create a snapshot of the context, and then if there's an error, we should restore this. Actually, we should take a snapshot before each here. There we go. And before we return the success, we should restore the snapshot. Now this doesn't exist yet. I haven't made that functionality, but it's a pretty simple thing. So basically we can create a snapshot. Which I guess would just be, it would just be like a copy here. So we're just copying ourselves, and I'm not gonna worry about errors. That's not gonna change at this point anyway. And the reader is kind of has to be handled by each parser individually, so I'm not gonna worry about this either. So it's basically only concerned with the line and column and the file. These three are the ones that gonna change. So we just put a snapshot there, and then we have a restore function, which we take a snapshot and just set those things. So we set this to file and line and column. All right. Cool. And take while, that's right. So we're looping through, we're creating a snapshot, we're running the parser. If there was an error, we restore it back to where we were, because now we're done parsing, and we should not return an error because we wanted to see how many items we get. We report success with these values thrown now into a slice, and we and then each time we have a success, we get a value and we append it into the list. So now we should get like a list of values every time. So now we have kind of like this loop going on. So let's now try and use that. So now I think we're ready to do actually, let's get rid of this one. I think we're ready to do parse number. All right, so parse number. Yeah, we need allocator. We don't really need. Well, we could add, like, you know, the comp time type on what type of number we get, maybe. I'm just gonna say it's U8 for now, or U32 or something, or no, F32. Yeah, F32. All right, so let's see. So we probably okay. Well, we want to parse some digits, I guess. So we'll grab. Okay. So I think we want to return a. Let's do expected message is number. Return a map. So we want a map over. Hang on. So this takes a digit. Now let's see. No, wait. No. This takes a list of digits and turns them into F32. Right. And I mean, we don't really need to read them as digits. We could also read them as they are, like a string, and then use a built-in function to turn it into a floating point, because there's like a standard is it format parse float? Yes. So you can also use this, which also has built-in like T. So you can also do that. Yeah. So probably we want to do that. So let's have a string here. So we want to parse a. Okay. Now this parse string is like saying that you need to have this string, but I want to have a parse. No, yeah, take while. Yeah, it's just take while parse digit, except we don't want to convert it into an actual digit, I guess. Is it doing that now though? With the condition is digit, take one. No, this isn't converting it actually. We lost the conversion here. So this is perfect then. We're parsing a digit, we're getting a actually we get the ASCII version. Okay. So that's fine for this purpose. So let's return that. So we'll map that over parse digit. No, it's not parse digit. This is going to be take while allocator parse digit. Yeah, and there was no expected message that we needed. Or so we're taking while parse digits, so we get a number of digits. We're mapping over those to parse a float from this string. And apparently we don't need to pass in a message. You don't need a message, but you're just mapping over this list. This could be an empty list. This is gonna throw an error if there's gonna be one. Okay, I guess. Okay, well, what you could do is add a condition here to say that, well, we want this to be at least one length and contain a digit. I guess you could do that. Because it's kind of weird that you're saying parse number and it might not find any number. You know, you have an empty string, but it's still successful. No, it won't be successful. If it's empty, it's gonna crash here. Yeah. Okay, well, actually, I think that's what we need to do. We need to sort of... Well, this is gonna crash. We kind of need to make sure it doesn't crash before we call this function in that case. So we should need to add a condition to this as well. But let's just try this now. So now we have parse number, and we're parsing a number 123.5. No, we can't do 0.5 because we're using parse digit. That's right. And we're taking, no, we just do this. Oops. I'm pretty sure, yeah, just the allocator. And we should get a number out. Yeah, we should get an F32 out. So let's do that. We get yeah, some errors. Oh, I see. This can be an error. So oh yeah, it doesn't crash. We get an error. I guess we can return none. Maybe. Does that work for? I wonder how this works for floating point. Like it has to take up a space in the bits. I don't know. Anyway, let's see. So we return this. Yeah, this needs alignment cast. Oops. Okay, expected void found string. Oh, this is T. And there we go. Now we can read variable length numbers. Okay, cool. So let's add a condition here now. Condition to this. Condition. Wait. Oh, there we go. Alright, condition. I will need a predicate function. This is kind of like a lambda in you know, in Zig, but it is kind of clunky. Okay, and then expected message at the end. There we go. Okay, so you are going to be checking. So we could do like length should be more than 0, and I guess we can parse float there as well. So we cast away the result, we catch the error, and we will actually catch return false, and then we just check. No, that should be everything, and then we return true otherwise. Oops, where were? So we're parsing here. If it's succeeded, we return true. We get down here. If it fails, we return false, and then in the mapper we actually use the value. And here we should get like unreachable here. Actually, this should be unreachable. Oh, there's no comma there. Access of union function while field type is active. Oh, I've sent in the wrong thing here. So you allocator predicate function, parser, and then expected message. Oh yeah, I forgot to do this. There we go. Type in special predicate function, expected F32 actual string. What? Oh, no, okay, this needs to happen first, right? First we do a condition on this one. There we go. We do a condition on this one. Okay, there we go. And then when we know it's a float, we do the map. Okay. Expected unit found string. Okay, let's do like report error 84 309. Oh, I see. Okay. Actual This is okay. Actual, I mean, we could put like actual format, I guess. It complicates things here. Or we could just have a function also that turns it into the correct format based on the type that you put in, maybe. I don't know. Let's just do actual format, and now we need to put this here. You are a string, or I guess S. You are a character. There we go. All right. There we go. So now we should be able to say, okay, well, there's no number here. Okay, and the actual is empty because there was no numbers being read, I guess. But yeah, now it's like, yeah, we didn't find a number. You have to have a proper number. And we can have like any length number now. But this won't fit, right? Okay, I guess it kind of works anyway. But the 0.3 doesn't work. And for that, I think, yeah, we need to add like 1 of for that to work. And 1 off. I mean, it's kind of 1 off is kind of like a sequence. Let's copy this. So the idea of 1 off is that you would pass in any number of parsers, and then only one of them, only one of them needs to be true, and so, or needs to succeed, and when it succeeds, you will. I just thought of something. Maybe all the parser functions. Maybe the result should be the same. I don't know. Because the issue here is the result. Like, what should the result be? Should it be one of the parsers? Should it just be void? I mean, the easiest way to do this is to say that, yeah, it should be void. And yeah, then we'll go through each of the parsers. We will run it, check if there's an error we don't return. What we do is, I think we need to store the errors in a list, error results. No, this is parser results void dot empty. Okay, if we have a success, we will return report success void. if we have an error, we will store the error in this list. We can do this. Okay, we store it there. Now if we get all the way at the end here, we don't, there's not a success. This is an error now. So we will return report error, except we do this. And then the error has we kind of want to merge these error results, basically, I think. Maybe. Maybe it's not parser result void. Maybe it's parser result error. Parser error message. And so this would be, actually this would be like append slice. All right. And let's see, report success, append slice. Okay, so at the end we return an error. And then the messages is gonna be error results to own slice. Yeah, so it's sort of like a maybe you could say it's like an inverted sequence or something, because you're trying everything here. Also, yeah, between each run we need to have a snapshot as well, because if there's an error we need to restore the snapshot. Yeah, and then we'll try the next one on the same place. And as soon as you get a success, then we go through. Actually, I just realized that the snapshot restore doesn't really work too well. I mean, if the reader has advanced, which it can do, like say you have a sequence where the first one succeeds and the next one fails, well then the reader actually progressed with the first one. Can you restore readers? So that's gonna be an issue. I need to do that. Restore reader as well somehow. I'm not sure if you can do that. Because you could progress arbitrarily far along this reader, and then you can't just backtrack to where you were. You have to have like enough buffer to do that. So that is an issue. Yeah. Because the buffer can be flushed, and then you but yeah, you have to have like maybe a reader that can be either. You don't want to reset it though. Maybe we shouldn't have used a reader. I don't know. Yeah, we'll have to figure it out. Okay. Where were we? One off, right? Yeah, so yeah, that should work. Okay. Now we go to the number and we say here, this is like the sort of, you know, yeah, and what's nice here is that you can do this. So you can say, okay, well, I want this to be the sort of character parser or byte parser, and this is gonna be one off parse digit or parse character, which is the dot. And it is a little bit more, you know, advanced than that, because there should only be one dot, and also you have to, well, I guess you don't have to start with a digit, but yeah. So you could do this. So you could define this parser like this. This is like one of the strengths of this type of programming. You can just define this here, and then we'll just put this here instead. This is the byte parser. There we go. And then everything should be the same. And we'll see if we got any errors, which we do. Oops. Okay, I'll do a little bit more here, then I have to leave here, but it's getting a bit late for me. Error union is ignored. Yeah, catch unreachable. Easily fixed. Allocator, yeah, that's good. Context allocator. Mismatch of predicate function expected. List of void. Okay, you need C. Okay, now you're complaining about a list of void. Right. Oh yeah, we need the, okay. We need the value of this. That's the issue here. Okay, let's do this just for convenience right now. Let's change this into, well, what we could do is we could actually say that, okay, the result type should be the same for every parser. And then, so just to make this convenient, so then we actually have a T, and we could just report success with this value that we get out here, because it's guaranteed to be a T here. Actually, we could just return result directly. Okay, and now we can specify that this is going to be a U8. Cool. But we still only read 4153, okay. Okay, so I'll fix this and then I'll call it here. Let's see, one of what is going on. Okay, this no, so the first digit should fail. So then we restore, we append the error message there, and then the digit should succeed, right? For exercise 74 of ziglings, we're given one comp time. We don't need one. The exercise compiles without issue, bug, or intended. I wonder. I think some of them were skipped. I don't remember which one, if 74 was one of them. But I think that one you have to... Well, what I would... I think I remember to put comp time in the parameter of the function, I think. That the function that used the integer for array length. Is it that one? Or is it... I guess I can go in here and check 74. Yeah, I think I did this. So you're saying it works without this? Well, okay. Did you try to add it? Did you add it first and then compiled and then removed it and then it doesn't complain? Because once you've passed it, it doesn't report the errors anymore for the previous ones. So if I do this, there's no errors reported. Oh, you didn't add it at all. Okay. It might be because it's called from a comp time only context, and then it's not needed, I guess. Yeah, probably. All right. Why is this happening? Wait. Yeah, we're going through all the parsers. And did I add it to the wrong, to this correct thing? Parse number. Yeah. There should be one of, so it should be either this or this. And no, not here. So I wonder if that's a bug or intended to show it's not needed to put count time everywhere. I'm not sure if maybe it used to be, maybe because things have changed, so this ziglings has been like updated every version. And this might be one of those cases where this could have been, maybe you would have to put comp time here. But I think you don't have to, because this is a comp time context. So when you call this function, it's in a comp time context. So everything is comp time, which probably make this comp time in that context. But if you would call this function in from a non-comp time context, then I mean, I don't know if this is the case, but I think yeah, definitely if you call this from a non-comp time context, then this shouldn't work, because this needs to be comp time known, and this is runtime only. So I don't know, but yeah, this is definitely, this is like, all of this is comp time known right now. But if you would call this, if you move this code in the main, into the main function, if you move this code into the main function, then I mean, what does it say here? This values type is size known at compile time, but we're letting the compiler infer both from the return type of a function. And here's the function. Note that the return type value depends on one of the input arguments. Okay. Yeah, I don't know if this could be a mistake. Can no longer be carried out as this, since the compiler has been improved, which automatically sets comp time when necessary and no longer causes errors. Therefore, it will be skipped until we find the reproducibility. Okay. Oh, did you see that? Was there an issue there? Okay. Well, that explains it. Cool. All right. Okay, this baffles me a little bit. I'm trying to stare at the problem here to find a solution. Found issue on ziglings. Okay. Yeah, sounds about right. Yeah, the comp time stuff really tripped me up in the beginning. Like, it took a while to get adjusted and get a intuition about how to use it and stuff. And it's still, you know, it's things happen that you're like, what the hell? How do I fix it? Like, I mean, this shouldn't really do much of anything right now anyways. We're appending. If there's a success, we return the result. We should be running both of the parsers. I guess we could log out one of parsers closure parsers. Yeah. This doesn't really help me unless I put a name to each parser, I guess. I mean, I guess I could do that. could put like a label, and this is map, but actually we probably want to put, we probably don't have like the label like to put the label here. And then one off. I mean, this could just be one off, whatever. This is condition. No, let's just put this here, because we could do. Actually, yeah, no, let's not have label there. Let's just put this as map. This take while. Take one. Okay, and then we'll have a function called add label or set label. I mean, we're not mutating, we're creating a new. Wait, are we mutating? Yeah, we're probably mutating here. Okay. So let's get a parser. And that has to be mutable now, so okay, you know what, I'm not gonna do this right now. Oh my god, the label is actually, the compiler inferring that needs to be content goes against the idea of no magic. Technically, the compiler inferring that it needs to be content is hidden magic they avoid. I mean, yeah, I mean, you have to, I mean, you always have to have implicit things happening. I mean, yeah. I think the idea is that if, you know, if that's always going to be the case, why not always add it? Like, it's just for convenience. It's like, instead of you having to manually go and mark it comp time, it just adds it in there, because you always have to add it and like anyways. So I think that's the reasoning behind it. Now, but I don't know if that's true, but that's just my assumption of that. But yeah, it is true. Like a lot of things, like there is coercion. Okay, let's say you have like a number A here. That is a U32 something. Okay, and then you have a B, which is a U8, and no, wait, let's just have a U8, and then we have a U, and then we have an A, which is a U32. Now you can just set this to B, because it's gonna get coerced by yeah, I think they're called like widening the type. So that happens implicitly. However, if you have the other way around, C is a U8 equals A. Now here you actually need to do a cast. Okay, I don't get this error here, but you need to do a cast here. And the same goes for if you have like a floating point. Now you need to cast A to a float. So the only time you can sort of like implicit coercion happens is when you have like a lower size of the same type put into a larger size of the same type. And then there's some other ones regarding like pointers as well. But I think it's just for convenience. It's just like, well, you know, some of those things require, I guess the idea is also that it makes sort of the conversion in runtime be visible to you, and you see that it's there and it takes up space and computer time. But if there's like just an implicit you know, thing that happens anyway, that doesn't really, that it's just making you do something that is unnecessary, basically. So I think I like that, you know, thing. So that would mean comp time is actually a lower type than runtime. Lower type. Could you elaborate? Because I'm too tired to understand. I think. Okay. Why? Okay. Oh, you know what? Maybe. No, take while should take while it's a digit or a dot. It's not actually a time. It is time. It is in when the compiler runs, or when the compiler compiles. It's the time when the compiler runs and compiles, or it's the time when the compiler compiles the program. And runtime is the time when the program runs. Yeah, so that's the concept of comp time. Is like, it's not running in runtime, and the compiler can use the information in comp time to optimize things and stuff, and can evaluate types and values that is known in comp time, so you don't have to spend precious runtime to do that. This should just run this. Is there something wrong here? Now we just get the result. That should like run the whole one off and return a success. So the compiler probably creating two functions, one for compile time, one for runtime. But if you only use compile time args, it will only create the comp time function infer that needs to. Yeah, so if you don't call the function from runtime, the function won't end up in runtime, in the runtime program. And if you can import the entire universe of Zig, but it will only put the things you call from runtime, like from the main function, in the actual program. You can define any number of functions, but they won't end up unless you call them. But you're calling it from comp time and not from the main function. You're calling it from a comp time context. It won't be put in the runtime. It's not really, I mean, yeah, you can say it's creating two functions, but it's like the function that gets called from comp time is just created in comp time, and it lives only in comp time and gets evaluated there and called there and run there. Add the comp time for the variable for the function. Sorry, I don't know where you are. Well, let's hang on. No, where are we? One off. I will. Okay, so we're doing this. Let's actually log here. One of parser, and then this would be, let's actually do that, and then this is parser.label. Yeah, so it reads first 4 successes, right? And then this fails, so it reads this, which apparently also fails, probably. But if both fails, why does it fail though? So parse, this fails apparently. What? 3? Well, with only args that are known comp time. Okay, specifying comp time for the arg and the func. You're forcing it to run only at comp time. Yes. That is correct. Or rather, well, it's kind of more complex because you can actually have a, well, in this case, yes. You can actually have a function take values, like runtime values and comp time values at the same time. You can have like I mean that you can have one parameter that can be comp time, and then the next parameter is runtime. So you can have, that's how the print function works, for example. The first parameter is a comp time, like this function here. This takes a comp time string, which is the first one. So, and the reason for that is that it can parse how to build the string basically in comp time. And then you have args, which is runtime known. I mean, the type is comp time known, but the values are runtime. So you can have mixed comp time and runtime. And then the parts that are comp time, so basically I think that it like evaluates comp time stuff as far as it can, I guess. And then I guess it's all about like dependency. Like if something that is comp time depends on a runtime value, then that is an error. Okay, by the way, I know what this issue is, and it's the problem I was talking about before. The buffer, the underlying reader that we're using. Okay, I think I know the issue. So that we do take byte, take one. Okay, this one. Actually, we need a peak one instead. We need peak one and then consume it. Yeah. We need peak one here. Peak one. This only peaks. And we don't take. Yeah, and then we take one, but we don't care about the result. I guess we can make a skip and we'll take some number. This number can be stored here. No, pointer from int. And then we get the closure here. We grab closure and int from pointer. And we do skip. And we take. We don't care about the results. Okay, this is a void. Okay, but we want to do this n times. But I think we want to take this one at a time here. We don't care about I. Alright. Actually, we don't need to peek. We can just take, because it's the same thing. All right. We can also just have a take and, which just returns the string. Okay, so now if we do, let's see, parse, wait, which one is it? Parse digit. Hello, Lord something. What are you working on? Right now I'm working on kind of like a proof of concept, like parser, like a monadic parser in Zig. How are you doing? Let's see. So take one. Actually, we should just do. We should peek one instead. And then we do a sequence. Oops. Oh, you're doing Sig for 4 years. Wow. I've done about 1 year. So I did ziglings because I wanted to like cover the bases. Because I never did like the tutorial, and so I learned a few things from that. All right. So, what kind of projects have you been doing in Zig? 4 years, that's a lot. Okay, sequence. Let's see. Expected. Okay, yeah. So my idea here is that we will do this, and once that is done, we want to consume the thing, so we just skip one. Yeah. So once if this succeeds, we skip. So if this fails, we have actually not moved forward yet. Hopefully. I mean, yeah, peak. If you call peak several times, it should still, you know, it should still be at the same place. Yeah, does not advance. Yeah, that's the whole point, I guess. And oh yeah, this needs to be a. This needs to be this. Okay. Doing all sorts of projects must act in right now from a template engine tailored must be config files been also written at GUI engine. Board of it right now where I dot files are 4K lines of Zig and a bunch of other stuff. Oh, cool. Yeah. Hang on. Oh yeah, thank you for the follow, Alas Tegin and Lord Mazda. I don't know how to pronounce that, sorry. Yeah, I think if we look at this example here, this is from ziglings, and the question came up where apparently in the new version of Zig, this zigling exercise automatically is already completed, because in the old version you had to add comp time here to make this work, but in the new Zig version it infers this comp time. If you call it from a comp time context, I assume, you don't need to add this here. So if you call this function from a comp time context, then it automatically adds comp time here. And I was like, well, I understand kind of why. I mean, if it's like, it's nice because now you don't force this to be a comp time function. Actually, you have to have it the comp time actually, because this is a count. You have to use it here. But anyway, if it wasn't used like this, I guess, yeah, it's nice that it was comp time, because then it would be evaluated at comp time. Could be justified philosophy of functions being call blind as async functions, but in this case seems like the argument would always have to be comp time regardless. Yeah, in this case it's it has to be comp time since it's used like this. But yeah, but what if like we didn't use it like this? It just, you know, did some calculation and returned. Then it would be, you know, if you wanted to use it in comp time and not comp time, you would have to make like a copy of it and mark it as not comp time in one version and then comp time in another version, which would be bad, I guess. So I think it's good that it's like this. But it's also kind of confusing here because it's used like always, should always be comp time. But yeah. Yeah, I went through all of the 110 exercises in 2 streams, but the yeah, there was like async await stuff that, or async, I don't know if, yeah, what it's called, but it's like async stuff. There was like 10 lessons or something that didn't exist because, you know, it's not in the language now. But yeah, there's 110 exercises. So it's kind of daunting, like if you're new. But it's good. I should have probably done it the first time, but I don't know. I'd like to just jump in and start doing stuff in a few months. So will they release async with 0.16? Oh, cool. Nice. they postpone it again? Yeah, I guess we'll see. Okay, so now let's see where. Okay, so we got a bunch of things here. Let's see. You say something here. Yes. We need bind now. Okay. So we have map. Now we need bind. So bind. And we have a bind function. Okay. Now the result of the bind function has to be a parser function. So this will simply be this, and then we can assume that it's not void. This is bind function, and A will be oh hey MRK, how's it going? The async is definitely coming in 0.16, confirmed by Andrew Kelly 2 days ago. Whoa. Nice. Cool. All right. Oh, nice. The audio got out of sync with the video. It's kind of hard to tell. I mean, I'm just... Okay, now I'm selecting the bind here. I guess, okay, I guess you can hear... Oh, I see. Not from me. Okay. Let's see. Okay, so the return type of this function is a parser function. It's the monadic value here, or whatever it's called. A is supposed to be the parser element of this parser, so that's the input. And then we get B. Do we need this? I don't think so. No, wait. Yeah, we're checking if this function... Yeah, we still need to check that. Bind function. Oh, the async AI talk. Oh, okay. So bind function. Man, it feels nice to do functional programming in Sig. Okay, we're creating our own closures and you know. Okay, so this is bind and yeah, we need this. This should be okay. We'll see what happens here. Yeah, we don't need to store this actually. This is a function pointer that survives the closure here. Cursed comp time stuff. I like it. Yeah. The more you know delve into Zig, the more curious you get about this comp time stuff. So this returns, no, this returns this. So B is actually gonna be, this is gonna be like MB. Stands for monadic value B. But I do like to work in a programming language where there's actually hope of getting this done. Because I've tried to implement this sort of thing in TypeScript, but that was like, yeah, a nightmare. Okay, closure. Right, so what are we doing here? Bind takes a function which takes the value of this parser, eventual value, and returns a new like parser function. So if there's an error, we just return the error. If there is a success, we take the value. Right, we don't report. Now what we do instead is that we will get a new parser, which is like parser B. And we call bind function with the value. So now we get a new parser that we have to run. So we have to run this. So result B is parser B.run. This is like the usual pattern. And then we switch on that again here. If there's an error, let's see. Okay, how does this work with the rollback? I mean, it doesn't work with the rollback. That's the answer to that question. Right now, at least, I have to sort of fix that error first, but whatever. Let's see. Error. As long as you have the happy path, everything should be fine. And if you have a success, we get the value B out, and then yeah, we just return this. Actually, we could just return this result straight up. Yeah, we just return this like this. Okay. And okay, expected found use size. Okay, let's do an int cast. Actually, this should be like a bit cast, I think, because yeah, I don't know. Okay, now we're back here. Now we have the means to do this. Okay, I made a library once that basically replaced vtables with a comp time system that can, when given a list of types, implementing a certain interface. Assembly those in a tagged union with a tag for each implementer, as well as glue functions that can call respective implementation. That is the advantage that you can pass any type parameters and so on. And I use that in my GUI engine. Problem is that it was so complicated I usually couldn't explain to people. Okay. That sounds amazing, actually. I mean, also doesn't work anymore because it needs using namespace. Yeah, I also got burned on that. I was using namespace to more easy like import everything from a file and then export it, like export everything. But then you have to like manually do export everything, unless you have unless you want to live with having a namespace. No, but the thing is, in this case, I'm only using the pointer as a space for this int. This int is from the start is a U32, so I'm storing it here as a U32. And then I'm taking it back from this here. But I was thinking like I'm storing it as a U32, so I was thinking like, should I do an int cost or a bit cost, because it's already stored as it should be, I think. I don't know. Maybe not. Maybe this is better actually. Someone actually had a need to rework that thing where you're working without using names, but actually it wasn't a bad idea either. But I still think overall reasoning behind remote use of it, using names was pretty silly. I mean, I liked it because it allowed things like, you know, mix-ins and stuff. But I mean, it was a bit clunky. It wasn't. It was kind of like, it felt a little bit inconsistent to me. Like it only took the fields or whatever, or was it the other way around? I don't remember. Int cast good safety checks and debuggers. Yeah, I think int cast is probably best. The code design. I mean, the thing is, okay, so I could explain a little bit here. So I'm not saying the code design is perfect here, but what I'm doing is I basically have this like generic structure that has a parser function pointer, and sometimes the parser function has to have some extra data, you know, context. So we have an aniopaque. I mean, it's kind of like a v-table here, and you have this aniopaque pointer here, this closure. But in that case, like usually I do this, I create some space for something and I store it here. But in this case, wherever this was, where was it? Parse character, right? Or take one, parse. Yeah, no? Where was it? Int from pointer. Yeah, here. Okay. So basically here is like, yeah, okay. Well, this is, you know, it's a U64 usually. I mean, it's a U32 or U64 or whatever. It's 32-bit or 64. So I'm basically using it as storage just to so I don't have to allocate this. It's fine. It's fine. Okay. Well, okay. Now we have the bind function, and we can now say okay, what do we want to do actually? Hang on. No, yeah, but we could, instead of doing a sequence, which is very not powerful, let's do a bind, which is very much good, very good, very powerful, very good. Bind needs, no, it's just bind, not bind function. Bind needs an allocator, and then we need a bind function. Bind function, and this one takes a u8 and returns a parser function and returns that. Okay, now this is where I would maybe be able to use, like a DSL in ComTime to turn Zig into Haskell. Okay. Anyway, so let's do this. We will now. So we take this. So basically, well, now we can do that. We can do the predicate. Yeah, I mean we could do the predicate here if we want. No, we want to bind on this condition. Yeah, and then we return skip one. See, that's the power of bind. You take the value result, but now you can also determine what the outcome will be based on this input. Except in this case, we just return skip one because that's all we want to do. Yeah, so we have allocated by function parser. There we go. Yeah, okay, fine. I mean, you have things, you have what is called man, I mean, yeah, I know that there's like ancient libraries and programs in yeah, Bison, yeah. But I was thinking more like this. You have bind. In Haskell you would write okay. You would have, let's say we have this thing maybe. Okay, I'm gonna mix things here. Maybe U8. This is actually like a char, I think, or something like that. U8 and then you can say that b equals to a and then bind, and then you make a lambda to take the value and return, you know, nothing. And you know, I'm defining these functions to actually be able to do this. So what I'm saying is that I could make a DSL in ComTime here to say that, yeah, this is the source. Hang on. And then I can parse this and produce, you know, this glue here to make this work. So it's not only the parser comedy, it's the it's like, you know, it's the monadic language stuff here. But this is like, this will require a lot of stuff here. I mean, yeah, I don't know. I don't think it's gonna work yet because ComTime is too weak, partly due to things like removing using namespace. Yeah, maybe. Alright, so we're doing this crap here. Bind function, C, unused. Yeah, we don't care about the input actually. Except we do. This is the problem. Yeah, we do care about the input, actually, because we want to return this. So actually, we need to map you. Yeah. Oh man, I want the context here. Yeah. We need the context. Okay, let's change this. Let's change this to be, so the first parameter is the context, the second is the input. So when we call bind, we actually put the context in there. There we go. Because now we can access, well, we can access a whole lot of stuff. Now we can access, but we need this for the, we need the allocator here. Okay, and now we need to map yeah, you can do code gen stuff using the build system, yes. I've done that before, but not like this though. But it's technically possible. I mean, you could just produce a string, which is the sig code, and put it into a sig file and compile that later, like generate code. But you can also parse this in comp time and maybe call these functions. But the problem is the types, I think, maybe. I don't know. Anyway, okay, so here we need the mapper function. So we will have the input is void, and then we just return C. Oh man, no. We don't have C. There's no closures. But we can do a const. We can introduce another concept. Another function is called const. Except you can't call it const. Constant. Okay. And value, as long as the constant, no, we need to create space for it. Value and the parser. So basically you're taking a parser and you're saying, hey, whatever you're returning, throw that in the trash, and I'm gonna, this is the value that you're gonna return, basically. And so we don't have a return type, we have type of value. And then this is the type there. We don't have a return type. I guess this would be type of value. And then we don't really have this, so we can remove that. The closure, we have to create the parser. We have to create the parser and the value. So I'll create a struct here, C for closure, value, and parser. And then we'll create a C, and we will populate, and then U will be a C pointer. I refuse to ever use that feature. Unless I have to, you know, use it for dealing with standard library. All right, or tuples. Okay, so C is this. I do understand why it's needed. It's good that it's there, but I won't. You know, I'm never gonna use that for my own variables or functions. Okay, so this is now stored over here. We grab it out there. Now this one is the closure thing. Closure C, we could call it. Closure C. And parser run. Okay, so we got the parser, but here we just return closure C value. All right. And right, so this one we don't use map, we use constant, and the value is C. There we go. Oh, A is not used. Okay, let's remove it. Value. Yeah, that's just, we don't need it, so. Wait. Oh yeah. We need to have like an error. Wait, this doesn't make sense. No, this is not MB. This should be parser results. Get parser elements of MB. There we go. Yes, yes, yes. Okay. You really like that feature. I remember there was a time where you could have null bytes in identifiers that would crash. Oh, okay, that is a very good use actually in marking. You are correct. What the hell am I doing? Okay, I've got no errors left, so I have no guidance anymore. Okay, let's go back. So we're trying to parse a number. There you go. It works. Woohoo! We can parse numbers with dots in them now. Awesome. And you know, if I add another dot, then parse float is gonna flip out. And it's, yeah, it expected a number, but we got this weird thing. Okay, cool. All right. How we calling the compiler? I install Overseer, the plugin Overseer. Then I do this, and you're done. Very good plugin. Yeah, and there's also the compiler NVim. I've never used that, so I don't know how it works, but that also uses Overseer. It seems. Okay. Okay, let's remove this debug log thing. There we go. Cool. Your new config has 3,000 lines with 1,500 of those being Zig, and it doesn't have this. Oh, cool. You have Zig in your config. I only have Lua. I don't think I have three. I don't know how many lines of code I have actually. What? Yeah, okay, so because, well, is Lua or is... Yeah, because Lua interfaces very well with like C, C++, I believe. It's like ran from C or something. And then you can... Okay, that sounds like Mojo stuff to me. Let's see what. Okay. Well, okay. What now? I mean, I said that I should quit here, but we're on a roll, so. Yeah. Okay. Well, now we can do things like. But I wish this would, you know, if you could, instead of doing this, you could say, you know, I mean, this is just this digit, to be honest. I guess this would be like, we could, I mean, you could do this. You could do function is digit. Actually, we could just, yeah, we could just put this here like this, right? There we go. And this one, yeah, parse float. Let's just make a function here. But this is different. This is catch, reach, return false, catch unreachable. It sounds very, very cursed. Okay, parse float. Unsafe. I like to have functions called unsafe in my code. Parse float check. I guess is float. Is string float. because you have no overload. There we go. No, this is a bool. False. Wait. No. Return false. Return true. It's just to make this a little bit more readable. And I'll just call this parse float. String to float. All right. Whoops. This what So it's a little bit too much passing. I'm thinking of putting everything in a struct so that allocator would always exist, and you would have like self. Like you would have to put self here, but at least you could say self.map. I'm not sure if you can do that though. No, you should probably be able to do that. I mean, I don't think it takes an hour, to be honest, but I guess you might. You're one of those people that goes like deep dives into it. I mean, I didn't put an hour into it. I just installed it and it works. You just have your you just have your commands. I don't bind them to anything. I do this. I type every time. I type :ot tab. That's it. And then I map some command, and then we're done. So :ot tab overseer toggle brings up the like task, this thing. And yeah, and then you can hide it. And that's all you need to do. I mean, you can set up a whole bunch of, you can set up like pre-configured commands that you can run or whatever. But yeah. And custom like error parsing and stuff for diagnostics. It can report like diagnostics to NeoVim if you set that up. Does my NeoVim config sound like you can actually expect anything to just work? I don't know, man. What are you using for? Did you roll your own plugin or plugin manager or? I see, constant. Okay, well this is actually not an issue. Okay, whatever, let's just make this. Let's just do this then. Okay. Yeah, so a little bit, if you don't, have a lambda, quote unquote, it looks a little bit better. But also this is bad. Maybe I should change this right now, actually. Parser context. Okay, let's do this. Let's do parser builder. And we'll just put everything here. Except this. I mean, I guess yeah, I just put everything in here. Everything that needs allocators. I know I'll have to do that because the compiler. Okay, I won't do that. String to float. I'll just group these together here. Okay, there we go. That's the last one. Okay, now everything that has an allocator. No, allocator. So we have part function, part function, and then this allocator. Let's capture. Oops. We'll say self parser builder. Okay. Yes, yes. Wait, I thought there were more. Oh. Okay, well. Oh, yeah, we don't need allocator now. Okay. You yourself. Parser builder. Serve. All right. Let's just add self to everything in here. Fine. All right. Now what the hell is your problem here? Now we can say self.allocator.create self.allocator. No, we need self. Get rid of that. And a pass. No. We say self.manage. Self.condition. There we go. take one. Certainly don't need you. Okay. Are we done? It felt like I did some edits that was bad here. Okay. No? Okay, I guess that's fine. Alright. So now here we actually have to get builder. I'll just call you B. Alright. Okay. Here. So yeah, just the parse number. Oops. Now we should get a whole bunch of errors. Yes. Okay, one off. Oh, I see. Self has to be first. I see. Yes. Even if it's comp time. Oh. Shoot. Well, that's not an issue actually, because we can make a new builder here. We can say parser builder init. And then call these. Alright. As long as you have an allocator, it's fine. Cool. Are we done? There we go. Alright, so it's a little bit, you know, just to make it a little bit less of a whole bunch of stuff you have to pass, like allocator everywhere, and now you don't have to do that. Great. Alright, well, yeah, I have to stop now, I think, but yeah, that was fun. I mean, doing the ziglings to kind of brush up on some Sig stuff and cover all the bases with some new knowledge. I mean, this wasn't that much that I learned, but it was some of the like there was some few tricks. What was like I lost it now, but it was like the continue expressions with while loops and Oh yeah, that the compiler fills undefined values with like hex value A. Very nice, because I never knew where that came from. So now it's like, okay, well, it means that I forgot to set something from undefined. So that's pretty nice. And I've got to do some stuff with this parser. It was just, you know, sometimes I get some itch to just do some kind of weird project like this, and I don't know, I just really like building these parsers and trying out new languages to build them in. And also this is monadic, and yeah, it kind of works actually. I mean, it's a little bit clumsy, but it does work. Alright, but anyway, yeah, that's gonna be it for this time, and yeah, hope you have a nice continuation here today, and I'll see you later. Bye bye.